Hello everyone and welcome to this new course or presentation on electronic captors or sensors. Sensors is another word for electronic captors. So for example, when you have a detector for water level, you can have different types of sensors for that. Okay, a simple type is the conduction detection, which means that when you have water at the level of the sensor, you would get a short circuit between two roads, two conducting lines, okay, two wires, electrical wires, and that short circuit would illuminate on the board that the water level is at here, is at the level of this sensor. Why? Because it has short circuited the wire. It has closed the electrical loop. Otherwise, if there's no water, it would be an open circuit. So this is a simplified example and a taste for the things to come. Chapter 1 or Module 1, Introduction to Electronic Sensors and Measurement Systems. Okay, as a definition for electronic sensors or captors, an electronic sensor, also called a captor, is a device that detects or measures a physical parameter or a physical quantity such as air pressure, temperature, humidity from the environment and then converts it into a measurable electrical signal. That can also be digitized. It can become electronic or numerical, okay? Now, sensors act as an interface between the physical world and electronic systems. So, these are the devices that relay measurements or presence or absence for different parameters in that physical world. It relays them, it converts them to electrical signals that can be actually processed or detected or understood by electronic devices, okay, by electronic boards. They transform various physical variables such as the following. You have temperature, pressure, light intensity, magnetic field, acceleration, and chemical concentration. You would have multiple things here, even more than what is already available, okay? But these are mainly some of the things that would most be occurring in a scenario where you would need to get measurements from the outside environment, okay? Just like, for example, in an airplane, you would need, and even in a car, you would need a temperature measurement for the engine so that it would fire a lamp, an alert, okay, or a warning in case something wrong is happening with the engine or the engine is overheating or is on fire. You would need that type of sensors. And we're going to understand how different sensors work, how they can capture the physical environment in order to relay it to an electronic board and eventually to a computer that would be able to process the kind of information that it is getting. Now, the physical parameters that we've seen on the previous page would be converted or translated into electrical signals that can be processed and understood by electronic boards and eventually processed by a computer, such as voltage, so voltage change, current, resistance, capacitance, meaning that the capacity would change due to, for example, the distance between these two facets that are holding the magnetic field, these two barriers of plus and minus charges. Okay, they are charged. You know, the capacitor has two facets, metallic facets that are charged plus and minus oppositely. So when the distance between them grows, it can change the capacitance. And this can detect like the change of distance between two barriers, for example, where you have placed that capacitor, that magnetic field. Now, and also the frequency, meaning the change of the frequency can be interpreted as the change, for example, of the RPM, the revolution per minute, okay, the number of revolutions per minute for an engine or a generator. Now, for the resistance, for example, this is one of the ways it can work. Resistance is often used to detect overheating and the change of temperature. Why? Because the conducting material okay, the conductance of the resistance changes when the resistance dilates. Why? Because the substance that is necessary or responsible for the conduction of the current from one edge to the other, due to dilation, it starts separating from each other, all right, which increases the resistance and allows less current to flow through that periphery, okay, through that resistance. So you can imagine if you have a fire, you would get an open circuit, okay? An open circuit meaning that the resistance would snap completely. Due to dilation, it would open the circuit and no current would flow at all. Now, in lower temperatures, the substance, like the conductive material that is within the resistance, would be contracting against each other. It would get much closer, allowing more current to flow, so you would get a lower resistance at lower temperatures. This is how basically the resistance would work. Now, mathematically, the function of a sensor can be expressed as a transfer function. So you have an output, which is Y, electrical output signal, is a function of a physical parameter, which is X. Okay? So, and X is changing in a specific way, following a specific equation or law. It might be linear or non-linear. Okay? So Y equal f of X, where X is the physical input quantity, such as temperature, pressure, airspeed, for example, and Y would be the electrical output signal, which is the conversion or the translation of the mechanical or physical parameter into an electrical pulse or signal or frequency or voltage. For small variations around an operating point, the relation can often be approximated as linear, meaning that you can represent the change or the relationship between the electrical output and the physical parameter as a line, given by the equation Y equal Sx plus B, where S would be actually the sensitivity of the sensor sensitivity. By the way, mathematically, S would be rise over run, which is the slope of the tangent, okay? The slope of the tangent, how much angle there is between the tangent to the curve. Here we have a line, not a curve, okay? But the line would be the same as the tangent to the curve. So how much angle there is between this line and the x-axis, and B would be the y-intercept. Mathematically, here physically it is the offset or bias. Sensors are fundamental components in modern technology systems such as industrial automation, aeronautics or aerospace, robotics, medical instrumentation, and consumer electronics. Role of sensors in measurement and control systems. Sensors play a critical role in measurement systems and automatic control systems. They allow machines to perceive environmental conditions such as robotics in an industrial factory. They can perceive humidity, pressure, temperature, etc., so that they would automatically know when to stop pushing or when to release something based on the application, of course. For example, let's say you have an industry for food. So once the temperature is enough for the thing that is being baked for mass production, okay, then the heater would be automatically turned off. This is a simple example. Like the furnace, correct? The oven, rather. They allow machines to perceive environmental conditions and react accordingly. In engineering systems, sensors are used to monitor physical variables, such as, again, temperature, pressure, humidity, etc., provide feedback to control systems so that they would know what should be done next automatically, and ensure safety and stability within the environment, also enabling automation and automatic decision control or decision making for the machine. In a feedback control system, the sensor measures the output variable and sends information to the controller. For example, consider a temperature control system. E of t, which is the error signal, is equal to the difference or excursion between the reference temperature, which is the real temperature, and the measured one, Okay, R of t is the reference value, temperature, and Y of t is the measured temperature from the sensor. So the difference between these two would give you the error margin. The controller then adjusts the actuator to minimize the error. This principle is widely used in thermostats, industrial process control, aircraft autopilot systems, and automotive engine control. Basic measurement chain. A typical measurement system consists of several stages known as the measurement chain. And you notice here that they are sequential. We start at first with the physical quantity, which is the parameter that needs to be measured, such as temperature, humidity, pressure, etc. And it would be detected by the sensor. And here, again, you notice that we have a sequential number of stages that are being sequenced one after the other. This is why we call it the measurement chain. Then, after the sensor detects the signal, you have signal conditioning, which is the adaptation of the signal, for example, amplification, noise filtering, okay, to clean the signal. After that, processing, which can mean that we are taking this a sample of the signal to average it, and this sample would become also quantized. Quantized meaning from this entire sample, I'm taking only one value that can fit on a scale, on a finite scale, because with analog signals, you might get an infinite amount or number of values. You can get 0.00000 all the way to 1, okay? I cannot deal with an infinite amount of values. Otherwise, I cannot, we wouldn't be able to code them or convert them into a binary code to be read by the computer. That's why I need to process it. I need to quantize it to set it at a fixed value. Then you send it to the output all the way to be received and processed by a computer or an electronic board at first. Then, it would be processed after that by a computer. Physical quantity. This represents the variable to be measured, such as temperature denoted by T, pressure by P, displacement X, which is when something moves from a reference point. This actually can be detected by using a phenomena like a sonar. So you can use ultrasonic frequencies, and we measure the time that the signal, that it took the signal from going from the sender, okay, all the way to the obstacle and then came back. So 2D equal velocity multiplied by the time lapse that it took the signal to go from the sender and then come back to the receiver, which are placed on the same head. So through that, I can measure the distance, which is the displacement, okay, because I can compare it from the original distance when there's motion. You have also the velocity, which is how much distance it's being incurred in terms of time. So they are correlated with each other. And accelerometer also, which is how much the velocity is changing. That would be also a unique sensor usually, okay, working with a gyroscopic instrumentation. We're gonna get more of that later. Sensor or transducer. The sensor converts the physical variable into an electrical signal. For example, you have the thermocouple output voltage is equal to V equal alpha, which is the Seebeck coefficient, multiplied by the differential of temperatures, T1 minus T2, where T1 and T2 are the junction temperatures. So, where you have a difference of temperature, this is how you can get the voltage, which is called the thermocouple output voltage. Signal conditioning. The raw signal from the sensor is usually weak or noisy, so it needs filtering, among other things, and requires conditioning such as amplification. So if it's a very low current, it needs a boost by an amplifier. It needs filtering from the noise to clear the noise up, linearization, and finally analog to digital conversion, which we've already talked about, okay, ADC. analog to digital conversion. So an example of that would be sampling. Okay, this is one of the stages. So you take one sample of the analog signal, then quantization. From that sample, you need to quantize, meaning that one value needs to be taken according to the scales, according to the existing values that are coded, okay, so that you would have limited number of values. Then this value is coded and converted into a binary sequence, a binary code. The amplifier gain is given by V out is equal to G times V in when we're talking about an amplifier, where G is the amplifier gain. Processing. The conditioned signal is processed using electronic circuits, microcontrollers, or computers. This stage may involve digital filtering, data analysis to analyze what the received value from the sensor means. For example, when you have a very high resistance coming from a thermistor, it means fire, right? Like when you have, or let's say I'm detecting the current that is going through the thermal resistor. If the current is zero or very low, it means either fire or overheat, okay, close to fire. Fire would be an open circuit, which means that no current would flow at all. Or if the current that is flowing is actually of a good value, of a nominal value, it means that the temperature is nominal. And finally, control algorithms to process, like to, based on the processed value, make a decision to activate something, okay, so as to respond to the values being received from the sensors. Output, the final result may be displayed on screen, sent to a controller, stored in a database also for data collection for a future reference, so to speak, and for history, and used to actuate a system, meaning that the sensor output would also become an input for a control system to actuate a system, to activate something. As an example for something being displayed on the screen or a screen display, you would get an engine oil check on your dashboard within your car when you have a problem with the engine, such as an overheating or high oil temperature. So this is coming from the sensor of the oil temperature, which is usually like an RTD, resistor checker, resistance temperature detector, okay? And it would be indicated on your dashboard that something is wrong, like there's a high temperature in your oil within your engine. Classification of sensors. Sensors can be categorized according to several criteria. You have analog versus digital sensors. Okay, so the analog sensors produce a continuous signal, continuous electrical signal, which is proportional to the measured quantity, right? For example, you have a pressure sensor. So when you have an increase of pressure, that increase of pressure would reflect as an increase of the electrical current. That would be an analog sensor. So in such case, you would get V out, the output voltage is equal to Kx, where K is the proportionality constant multiplied by X, which is the measured physical quantity. Now, since we brought up the pressure sensor, okay, this is one of the ways it would work. So let's say you have two metal plates that form the pressure sensor, which actually also constitute a capacitor. So when the pressure increases, the distance between these two plates, okay, one is positively charged and the other is negatively charged, the distance between them would decrease. This would reflect as an increase of the current. Meanwhile, opposite to that, when you have a drop of pressure, the distance between these two plates would increase, being reflected as a decrease or a decline of the current amplitude. Okay, this is how you would detect the change of the pressure in such case. Examples of different sensors, thermistors. which is again the resistance that changes of value. Its resistance changes based on the temperature of the environment. LVDT, displacement sensors, and strain gauges. Now, LVDT means linear variable differential transformer, which converts like the displacement into an electrical signal. It is a very high accuracy electromechanical sensor, okay, that measures actually displacement and converts the displacement into an electrical signal. As for the strain gauges, these convert the applied force into an electrical signal. Okay, so they detect the force and the pressure being applied to a surface. Now, LVDT, by the way, is often used in detecting the displacement of control surfaces within an aircraft, such as the ailerons, the levels, the elevators, etc. Digital sensors. Digital sensors produce discrete outputs, typically in binary form. Example, you would get an output of 0 or 1, which is false or true, off or on, or a digital word meaning a digital binary sequence, a code indicating one of the states of the sensor. For example, heated, mid-temperature, cold, inactive, something like that. The word would be like D equal Bn, Bn minus 1, all the way to B0. This is from the high weight of the binary word to the lowest weight, which is all the way to the right, to the most right. Examples, digital temperature sensors, optical encoders, and MEMS accelerometers. MEMS now stands for microelectromechanical system, which detects change of velocity or acceleration, and the tilt, which means the angle change. This is how they actually can relay the change of the angle to a video game on your phone when you're playing like a car race game, and you notice that as you tilt your phone, it detects it and translates it as a change of the steering wheel's angle, correct? This is how it works, by detecting tilt and the change or variation of velocity. Active versus passive sensors. Now, active sensors generate their own electrical signal without an external feed or external power. Example, the thermocouple voltage, which is V equal at the output, alpha times T1 minus T2. So other examples would be piezoelectric sensors and photovoltaic cells, which are the cells that are placed within the solar system, okay, that generate power from the solar energy. We have piezoelectric sensors and thermocouples that we've talked about, which is creating a current from the differential of temperature between two poles, between two conductors. Now, concerning piezoelectric sensors, this is how they work. They generate power as they are squeezed. So, when they are squeezed, the change of the magnetic field, so usually you would have, for example, a capacitor, and when it is squeezed, the distance between the positively charged and negatively charged plate changes. This distance, as it changes the magnetic field between the plates, and it creates an electro-induced effect, okay? Electrically or electromagnetic induced current, okay, based on the change of the magnetic field. It's called also electromotric force, which is given by E is equal to minus d phi over dt, which is the derivative or the change of the magnetic field phi in respect of time. So the change of the magnetic field in respect of time creates an electro-induced current. And this current is what is created actively by the sensor itself. It's not being fed from outside. Now, as for the passive sensors require an external excitation source, external feed. Example, you have the strain gauge resistance change. Delta R divided by R is equal to GE, which is the gauge factor, multiplied by the strain being applied. So examples, RTDs or resistance that are, resistance thermodetector, okay, detection of temperature using the resistance value change. This is what it means. So RTD is a real type of sensor that is basically using the change of resistance to detect the change of temperature, capacitive sensors, and inductive sensors. So capacitive sensors would have a current already applied to them from outside, and when that current changes, they detect a change of pressure, for example. Or inductive sensors, the same concept, it might be detecting the displacement, because as the inductor changes its length, okay, that would be an indication or indicative of the change of distance and the displacement. Okay, this is how they actually work, but they need an external power source in order to be, outputting the relay, outputting the measurement. Contact versus non-contact sensors. Contact sensors, these types of sensors must physically touch the object being measured. As an example, you have the potentiometer or potentiometric displacement sensors, the strain gauges, which means that when they are pressured, okay, they change in volume, or basically the distance between, again, the two differently charged plates would change based on the pressure being applied by the air, for example. And this is how they measure the change of pressure. And thermistors, which also would touch the air being measured, for example, or the liquid, and that liquid would change their resistance value. This would immediately reflect as a change of temperature. Advantages, they have a high accuracy, direct measurement, but also the disadvantages are that they wear out very quickly. Okay, they can wear out and they are prone to mechanical damage, and they have a limited time span. Non-contact sensors, these sensors measure variables without direct physical contact. Examples, infrared temperature sensors that detect the change of temperature based on the infrared signal, which we know this is the same wave that is connected to heat. The infrared frequency is associated with high temperature. So with high temperature, you would have a high signal of infrared, correct? You have ultrasonic sensors that measure the distance based on sending a wave, an ultrasonic wave, just like the bat works, by the way. This is how the bat maps the environment. It sends a signal, ultrasonic signal, and once it receives back the reflection, the reflected signal, it measures the time span, and based on this time span and knowing the speed of sound within the air, this is how it can assess the distance from the target to the sender, correct? So basically you have the sender and receiver mounted on the same head. An ultrasonic wave is sent, then once it's reflected and comes back, it applies, it follows the rule or the equation 2D, which is 2 times the distance is equal to the velocity of sound in the air times or multiplied by the time it took for the wave to go and come back. You have optical sensors, which is like the LiDAR, light direction and ranging. Okay, just like the sonar is the ultrasonic sensor, by the way. And you have radar sensors that send a signal, then receives back the signal, and by measuring the time, they can measure the distance. Advantages, there is no mechanical wear out, and they are more suitable for harsh environments. Sensor performance characteristics. Sensor performance is evaluated using several important parameters. First of all, you have the sensitivity of the sensor, which measures how much the output changes for a change of an input. Okay, so sensitivity is equal to the change of the output, dy, in respect of the change of the input, dx. High sensitivity allows more accuracy, okay, which is a detection of smaller changes. Even smaller changes would be detected and converted into beneficial signals, increasing the entropy of the sensor, so to speak. Accuracy. Accuracy indicates how close the measured value is to the true value. So it is given by 1 minus this quotient. Because here, this is a wrong assumption that accuracy is equal to x measured minus x true divided by x true. No, this is the error margin, which is the excursion or the difference between the real value, true value, and the measured value divided by the true value. Okay? It's an absolute value so that we won't have a negative answer. So the accuracy is 1 minus x measured minus x true divided by x true. So let's say you have here x measured is 1, x true is 2, for example, and the x true is true. It would be 1 over 2 or 50%. 50% difference, okay? That would be both the error and the accuracy, because 1 minus 0.5 would give us 0.5. But if the difference is very small, then the error margin would be small and the accuracy, which is 1 minus this error margin, would be high as 90%. Accuracy is often expressed as a percentage of the full scale. Precision. Precision describes the repeatability of measurements, meaning that whenever you would take the same measurement of the same parameter in the same conditions, they would give you the same exact value. Okay? So there are no fluctuations of the measurements, given that the physical parameter itself is not fluctuating. So it describes the repeatability of measurements. It is typically quantified using the standard deviation, which is given by sigma is equal to 1 divided by n, of course, square root on the outside, 1 over n, sigma from I equal 1 all the way to n. So for all the values, xi minus x bar, which is the value measured minus the average, okay, the mean value among all values, square, all the way divided by n, which is the total number of values, okay, and square root of that. This gives us the standard deviation. And this is how we measure the precision or the repeatability of measurements. Now here, as a side note, a system might be precise but not necessarily accurate, which means that every time you take the measurement for the same physical parameter in the same environmental conditions, okay, for the same circumstances, you keep getting the same measurement being replicated. So the system itself is not deviating. It's not like fluctuating, so to speak, okay? It's not being chaotic. It is stable. It's not unstable, it is stable. However, altogether, the system is not accurate, which means that all these measurements that are repetitive, that are the same over the time, they are not accurate because there's a wide gap between the actual value and the measured value due to one of the reasons, such as the sensor having worn out, okay, because of aging due to harsh environmental conditions. So there's an excursion, there's a gap between the measured value and the actual real value. Resolution. Resolution is actually the smallest detectable change in the measured quantity. So how much sensitive the sensor is. For digital systems, the resolution is equal to the full scale divided by 2 to the power of n, okay, which is all the values that can be detected, okay, and that are codified. N is the number of bits being used to represent that, the full scale of values. However, of course, not the full scale. The full scale won't ever be represented, but there would be a sampling of that scale, and the difference between, or the ratio between the full scale and the total number of values being coded and represented, this is what gives us the resolution. So n is the number of bits in the analog to digital conversion. Now, a small example for that, you would have a signal like this, okay? Now, this signal would be clipped by a square signal, And this square signal would clip different samples, okay, like this sample, this sample, this sample, this sample. And from these samples, you get only one discrete value, okay? So the number of values is 4. Meanwhile, the full scale is a completely larger scale of that, okay? So the resolution would be defined by, for example, you have 4 bits per second, correct? So that would be the resolution as a mild benign example, okay? But basically, it's the difference between the full scale, which is a large infinity of values, divided by the number of values that are actually represented. Linearity. Linearity describes how closely the sensor output follows a straight line relationship between the output and the input. So in other words, let's say y is the output and x is the input. The relationship between them would be an equation of a line equation, given by y is equal to ax plus b, where usually a is the sensitivity of the sensor, which is mathematically the rise over run, how much there's an output for a specific input, and b would be the bias or the y-intercept on the graph. Linearity error is given by EL is equal to y actual, the actual output, minus the yield, or like the ideal output, divided by the full scale. So as an example, let's say you have an input for which the output would be changing like that. It would no longer be linear. It would be non-linear, following a different kind of equation, such as a second-degree equation like a parabola, for example. It would no longer be a linear equation. At times, it becomes more complex to deal with. So we would rather prefer a linear type of relationship between the input and the output because it becomes more predictable. Hysteresis. This phenomenon occurs when the sensor output depends on the direction of the input change. Actually, this is when the output lags, okay, behind the input. So H would be equal, the hysteresis is equal to y increasing minus y decreasing. This phenomena is common in mechanical and magnetic sensors. So you would have an output increasing, but it's being delayed in respect to the input change. Okay? So the output is not in real time with the input, so it's lagging behind, which creates this hysteresis effect. In other words, the output of the system is not only depending on the real-time input changes, okay, not only on the real-time input values, but also on the historical input values. So it's also dependent on the historical changes of the input, not the input in real time. This is what creating this lagging effect within the curve. And this is called, by the way, a hysteresis loop, where the output changed based on not only the real-time input, but the historical input, the change of the input itself. Repeatability refers to the ability of a sensor to produce the same output or the same result under identical conditions. So if I have similar conditions, nothing has changed within the physical parameter, and I'm getting like multiple measurements from the same device, I should have the same results, okay? I should be expecting the same results. However, you can still get an excursion, okay, an error margin between different measurements, even when the system is highly accurate. So the repeatability error in such case is often expressed as ER is equal to the maximum distance between any of the values and the mean value, which is x bar. So it is max xi minus x bar. Response time. Response time describes how quickly a sensor reacts to a change in input if there's any lag between the input and the output. Many sensors behave like first-order dynamic systems, which is given by tau dy of t over dt plus y of t is equal to kx t, just like the pendulum, not the pendulum, the spring system, by the way, where tau is the time constant and K is the sensor gain. The time constant represents the time required for the output to reach approximately 63% of its final value outcome. Second module or chapter, sensor modeling and mathematical representation. In order to analyze and design measurement systems, sensors must be represented using mathematical models. These models describe how the sensor transforms a physical quantity into an electrical signal. Sensor modeling allows engineers to predict sensor behavior and the outcome, analyze errors, and design signal conditioning circuits. Sensor transfer function. The transfer function of a sensor describes the mathematical relationship between the input physical quantity and the output electrical signal. In general form, is given by y is equal to f of x, where f is the function of transfer, x is the input, which is the physical parameter variable, such as temperature, pressure, displacement, etc., and y would be the sensor output signal, which is voltage, current, frequency, or a resistance change. For many sensors operating within a limited range, the relationship can be approximated as linear, given by y is equal to sx plus y0 being the offset or the bias or zero output, s being the sensitivity of the sensor, which is also the slope of the tangent or rise over run mathematically. y0 would be the y-axis intercept. Of course, x here is the input or the physical parameter. If the sensor exhibits nonlinear behavior, the transfer function may be represented using higher order approximations such as Taylor series expansion, given by the relationship y is equal to a0 plus a1x plus a2x squared, etc. The transfer function is an essential characteristic because it determines how accurately the sensor can measure the input, which is the physical parameter being detected, okay? And how accurately this physical value is converted into an electrical signal. Static characteristics. Static characteristics describe the behavior of a sensor when the input quantity is constant or varies very slowly with time. These characteristics determine the accuracy and reliability of the sensor in steady-state conditions. So, is it stable or not? Sensitivity measures how much the sensor output changes in relationship with the input, given by S is equal to the variation or differential of the output in respect of the difference of the input or the input change. For continuous variables, sensitivity can be expressed as a derivative of the output voltage or output signal voltage in respect of the physical parameter input. So S is equal to dV over dx, where x is the physical input variable and V is the electrical output signal. Higher sensitivity means that small changes in the input would be reflected in the output immediately. So small changes in the physical quantity produce larger changes in the output signal. Offset, zero error. Offset refers to the sensor output when the input variable is zero. So V offset is equal to V when x, or the input value that's being measured, is equal to 0. A non-zero offset introduces a systematic measurement error, which means that you have an output signal being detected in spite of the fact that the input is 0. The measured physical parameter is not actually producing anything. And this requires adjustment and calibration. So there would be a possibility for the existence of a noise signal or an interference within the sensor or the receiving device. Linearity. Linearity indicates how closely the sensor output follows a straight line relationship with the input of a form V is equal to AX plus B. V being the output, X the input, A again is the sensitivity of the sensor, and B is the bias. This is an ideal linear relation, which is a line equation. V is equal to AX plus B. Linearity error can be expressed as EL is equal to V actual, the actual value, minus the ideal value, divided by V full scale. So it represents the excursion between, or the difference between the real value measured minus the actual value that's being measured. Okay, like the real value versus the value that's being detected, divided by V full scale. Hysteresis. This phenomenon occurs when the output depends on whether the input is increasing or decreasing. H, or hysteresis, is equal to V up minus V down. This phenomena is commonly observed in mechanical and magnetic sensors. Repeatability, which is another word for precision, describes the ability of a sensor to produce the same output given that the same input value is being applied repeatedly under identical conditions, meaning under the same temperature. For example, if we're talking about a temperature sensor, under the same pressure, if we're talking about a pressure sensor. So, now it doesn't mean necessarily accuracy, because it can keep producing or reproducing the same results, the same measurements, but all of these measurements are not actually accurate due to the sensor having worn out or the aging of the electronic device, etc. Now, however, or in all cases, it is often quantified using the standard deviation of measurements given by sigma is equal to the square root of 1 over n, which is all the number of measurements, sigma I equal 1 to n, which is the sum for all of the measured values, Vi minus V bar, which is the signal value minus the mean value for all the measurements, okay, like the current value minus the mean value for all the measurements square. Vi is an individual measurement, and V bar is actually the average value among all the measurements. Dynamic characteristics. While static characteristics describe steady state behavior for the sensors, dynamic characteristics describe how sensors respond to time dependent or time varying inputs. So in real systems, there would be a transition between a current state and an updated state. Sensors cannot respond instantaneously, okay, to an updated input or a change in the input, so there would be a transient behavior, a transition. Instead, they exhibit transient behavior before reaching a steady or stabilized state due to the change of inputs. It's not like a real time, yeah, it's real time, but it's not immediate, okay? There would be a transient change between the reaction of a current input, then another reaction to an updated input after that first input has been displayed, okay, or it has produced an output. So there's a lag, so to speak, between the input and the output. It's not like instant. Now, imported dynamic parameters include response time, settling time, stabilization, bandwidth, time constant, and rise time. For dynamic analysis, the sensor can be modeled using differential equations or transfer equations in the Laplace domain. If the sensor input is represented as x of t and output as y of t, the dynamic behavior may be described as f of dy over dt, so the change of the output in respect of time, y x is equal to 0. In control theory, the transfer function is often expressed in the Laplace domain by g of s is equal to ys over x of s, y being the output and x being the input, where x of s is the Laplace transform for the input, y of s is that of the output, and s is the Laplace complex variable, which is a transition from the time domain to the Laplace domain, to simplify the calculus or like the processing of the transfer function of the change between the input and the output. First order sensor model. Many sensors can be approximated by a first order dynamic system. This model is commonly used for temperature sensors, pressure, and many chemical sensors as well. The first order sensor is represented by the differential equation of the first degree, tau dV over dt, plus V of t, where of course dV over dt is the differential or the change of the voltage of the signal in respect of time, is equal to kx of t, where tau is the time constant of the sensor, k is the static gain of the sensor, x of t is the input for the physical variable, and of course V of t is the output signal. The time constant tau characterizes how quickly the system responds to changes in input. If the input undergoes a step change, which is the unit step function, x of t is equal to x0 u of t, where u of t is the unit step function or signal echelon, by the way, another name for that, the sensor becomes V of t is equal to kx0 multiplied by 1 minus exponential of minus t divided by tau. Important properties of the first order response. After time t is equal to tau, the output reaches approximately 63% of its final value. After t is equal to 3 tau, the output reaches approximately 95% of the final value, so almost stabilized. After t is equal to 5 tau, the system is considered to have reached the final steady state. Example, sensor sensitivity and transfer relation. The relationship between the sensor output and the measured physical variable can be expressed using the sensitivity coefficient. S is equal to delta output divided by delta input, which is the rate of change of the output in respect of the change of the input, or derivative of the output in respect of the input. Now, for infinitesimal changes, when you have very small rates of change, this is when we measure the derivative instead of the delta V over delta X, because the change rate is very small. So S is equal to dV over dx, where X is the physical variable being measured and V is the sensor output voltage. If the sensor is linear, V is equal to S times X. This simple relationship is widely used and accepted when designing sensor calibration procedures. Importance of sensor modeling. Sensor modeling is essential for several engineering tasks: designing signal conditioning circuits, predicting measurement errors, optimizing sensor placement also, and designing control systems. Also, simulating measurement systems in software to see how they would react and their behavior through or under different circumstances or conditions. Chapter or Module 3, Temperature Sensors. Temperature is one of the most commonly measured physical quantities in engineering systems. Temperature sensors convert thermal energy variations into measurable electrical signals such as voltage, resistance change, or current change. Temperature measurement plays a crucial role in numerous technological applications, including industrial processes, environmental monitoring, aerospace systems such as checking the temperature of the engine and detecting overheat, for example, or engine fire, and medical instrumentation. Temperature sensors can be classified into several categories based on their operating principle. So we have thermocouples, where you have two conductors between which you would get a differential of temperature between the two, and that difference of temperature would create a current or a voltage signal. Thermistors, where the conductivity within the material of a resistor would change due to dilation or contraction, which is caused by temperature change. So when the temperature increases, this dilation causes this conductive material to be set apart from each other, the molecules to become distant, increasing the resistance and reducing conductivity, leading to a drop of the current flow within the resistor, and vice versa. Another types, resistance temperature detector, RTD, semiconductor temperature sensors. Each type of sensor exhibits different characteristics in terms of sensitivity, accuracy, temperature range, response time, of course, and cost. Thermocouples. A thermocouple is a temperature sensor that operates based on the Seebeck effect. It consists of two different metallic conductors joined at one end to form a conjunction or a junction. When the junctions are kept at different temperatures, a voltage is generated due to thermoelectric effect, meaning due to the difference between the temperatures of both plates, of both metallic conductors. This is what generates a current of a specific signature, of a specific voltage, which depends on that difference. Now, what is the Seebeck effect? The thermoelectric voltage generated in a thermocouple is proportional to the temperature difference, as we mentioned, between the hot junction and the reference junction, to which we are measuring the difference. V is equal to alpha times T1 minus T2, which is T1 being temperature of the hot junction, T2 is the one for the reference junction. Alpha is the Seebeck coefficient, which is material dependent, so it changes based on what type of conductor, what is the material that we're using. And V, of course, is the thermoelectric voltage. The Seebeck coefficient typically ranges from a few microvolts per Kelvin. So alpha approximately is equal to 10 minus 60 microvolts per Kelvin. For higher accuracy, the thermoelectric voltage is described by a polynomial relation given by V is equal A1t plus A2t squared plus A3t to the power of 3, etc. The thermocouple construction. A thermocouple consists of hot junction, measurement junction, reference junction, which is the cold one, and two dissimilar metal wires. Common thermocouple types include type K, which is the chromyl or alumel substance material, type J, which is iron constantan, and type T, which is made of copper and constant. Advantages: very wide temperature range, so they can measure starting from minus 200 degrees Celsius all the way to 1800 degrees, depending on the type, of course, but still there's a very large range of measurement that they can operate with. Fast response time, so it's very prompt and immediate. High durability, so they are sustainable and they can last long. And also self-powered, which means that they don't need any external excitation or power source. Disadvantages: lower accuracy compared to RTDs or resistance thermal detectors. Requires cold junction compensation. Why? Because we are measuring the temperature based on a reference junction that needs to be cooled. If both of the junctions are of the same temperature, you wouldn't be able to detect the temperature change. And nonlinear response, which makes it more difficult or complex in order to assess the current temperature or measure the current temperature, because it does not follow the linear equation. Thermistors. A thermistor is a temperature-sensitive resistor made from semiconductor materials such as metal oxides. The resistance of the thermistor varies significantly with the temperature. Now, thermistors are highly sensitive and are commonly used for precise temperature measurement over limited temperature ranges. They are classified into two main types. You have the NTC and PTC, or negative temperature coefficient, and positive temperature coefficient. Negative temperature coefficient, NTC. For NTC thermistors, the resistance decreases as temperature increases, which is counterintuitive to what we've discussed before concerning the other type of thermistors. The resistance temperature relationship is described by R of T is equal to R0, which is the resistance at reference temperature T0, times exponential of beta, which is the material constant, multiplied by 1, divided by T, the current temperature in Kelvin, absolute temperature in Kelvin, minus 1 over T0, which is, again, the reference temperature T0. And R of T, of course, is the resistance value at temperature T. PTC thermistors, which is the positive temperature coefficient thermistor, works the same way that we've discussed earlier concerning the type that we've mentioned, where the resistance increase as the temperature increase due to the displacement of the conductive material, which is the metal oxide substance, and growing apart from each other, it increases the resistance, thereby decreasing the current flow within that resistance. This, leads to an increase, or like reflects an increase with temperature. These devices are often used for overcurrent protection so that it would immediately trigger a power cut, and self-regulating heating elements. Advantages: very high sensitivity due to the fact that they are detecting the temperature through a direct contact with the material or the physical parameter that we are measuring. Low cost, because it's simply a resistor of metal oxide material that can dilate or contract, and it has a small physical size. By the way, a simple example of what that would be like, it is, for example, used in the circuit breaker, where a dilation caused by an increase of temperature, which is triggered by an increase of a current flow, would trigger the brake or the circuit breaker to trip up to immediately cut the power from a line. Disadvantages: highly nonlinear response. You have limited temperature range, so they cannot measure a wide range of temperatures, and self-heating effects, meaning that due to overuse, they start self-heating themselves, even without a detection. RTD, or resistance temperature detectors. A resistance temperature detector, RTD, measures temperature by exploiting the predictable change in electrical resistance of metals due to dilation and contraction, which is prone to temperature. Most RTDs are made with platinum or from platinum due to its excellent stability and repeatability, meaning that it's stable. Repeatable, meaning that it lapses back to its original form after the temperature have increased and then decreased. It doesn't deform, so it is resilient, or in other words, it is elastic. It regains its original shape after having been exposed to harsh environmental conditions such as an overheating. The resistance temperature relation for the RTD is given by R of t is equal to R0, which is the resistance at reference temperature, times 1 plus alpha t, alpha being the temperature coefficient of resistance that is subject to the type of material being used, usually platinum, multiplied by t, which is the temperature that is being measured. For higher accuracy, the calendar Van Dusen equation is used, given by R of t is equal to R0 times 1 plus AT plus BT squared plus C times T minus 100T to the power of 3, where A, B, C are calibration constants. Typical platinum RTD characteristics: you have PT100, characterized by 100 ohms at 0 degrees, and PT1000, characterized by 1000 ohm resistance at 0 degrees. Advantages: high accuracy, excellent long-term stability, and good linearity. So the relationship is linear. Unlike the systems that we've seen before, they are more non-linear. Disadvantages: higher cost, slower response compared to thermocouples, so you have a lag between the input and the actual reaction to it, which is the output, and requires external excitation current. So it needs a current from the outside. It is not self-sufficient, not like the transducers that create, for example, the thermocouples create a current or a voltage based on the differential of temperature. They don't need an external source or excitation from the outside. Semiconductor temperature sensors. Semiconductor temperature sensors exploit the temperature dependence of semiconductor junction, voltages, or currents. These sensors are widely used in integrated circuits and digital temperature measurement systems. You have diode temperature sensors. The voltage across a diode junction varies with temperature. This is a beautiful characteristic that can be exploited. The diode equation is given by I, which is the diode current, equal to IS, saturation current, times exponential of QV divided by KT minus 1, where Q is the electron charge, V is the voltage, divided by K times T, Boltzmann constant, times absolute temperature, minus 1. The forward voltage decreases approximately linearly with temperature, so Vf is equal to Vf0 minus Kt. This property allows temperature to be determined by measuring the voltage drop across the diode. Of course, Vf0 is the voltage reference value. Integrated circuit temperature sensors. Modern semiconductor sensors integrate sensing elements, analog signal conditioning, analog to digital conversion or ADC, and digital communication interfaces, all in one device. Examples include digital temperature sensors, microcontroller-based thermal monitoring devices. The applications of temperature sensors cover a wide variety of engineering systems. This includes industrial temperature measurement used in manufacturing processes such as furnaces, chemical reactors, and power plants, and HVAC systems, for example, heating, ventilation, air conditioning systems rely on temperature sensors for climate control and regulation and energy efficiency, so reducing the overconsumption of power also. Another very important application is the aerospace and aeronautical systems such as engines and different devices on board. So aircraft and spacecraft use temperature sensors to monitor, for example, engine temperature, structural temperature on board, and environmental conditions. Temperature monitoring is critical for ensuring operational safety, system reliability, and energy efficiency in these applications. Chapter 4 or Module 4, Pressure Sensors. Pressure sensors are devices that measure the force exerted by a fluid, such as liquid or gas, per unit area. Pressure measurement is fundamental in many engineering systems, such as measuring the hydraulic pressure within an airplane or even within an automobile. So this includes industrial process control, aerospace instrumentation, automotive engines, and environmental monitoring. Pressure is defined as the normal force applied per unit area. P is equal to F divided by A, where P is the pressure in Pascal, F is the applied force in Newton, and A is the area over which the force is distributed in meters square. So the pressure is identified or expressed in Newton per meter square. Again, the international unit of measurement for the pressure is the Pascal, which is also Newton per meter square. Okay, it can be said in both ways. They both mean the same thing. In practical engineering applications, other units are also used, such as bar, atmosphere, which is in reference of the atmospheric pressure at sea level, or pounds per square inch, PSI, for the imperial, not metric, okay, the imperial system. Pressure sensors convert mechanical deformation into electrical signals by changing, for example, the capacitance of a condenser, of a capacitor, and this translates into a changing current, okay, or changing electrical signal. Pressure measurement principles. Most pressure sensors operate by measuring the deformation of elastic element when pressure is applied. Why elastic? So that it would regain its original shape once the pressure is released. This deformation may be detected using electrical techniques such as resistance variation, so it's not only capacitance, or capacitance variation, or piezoelectric charge generation, which means that the pressure would cause the plates of a capacitor, both positively and negatively charged, to move in respect of each other by changing the distance between them or enlarging the distance. So as the distance is shortened, the current would increase of voltage. So this would be translated into a higher pressure. When the distance increases due to a drop in the pressure, this would enlarge the gap between both plates, which would create a lower voltage tension signal or a lower current signal. So when pressure is applied to a flexible diaphragm, it produces mechanical stress and strain. Stress is defined as sigma is equal to F over A, which is the applied force per cross-sectional area. Very similar to the pressure formula, by the way. As for the strain, it describes the relative deformation of the material. So epsilon, or the strain, is equal to delta L divided by L, which is how much the length of a material has changed in respect to its original length. So epsilon is the strain, delta L is the change in length, with L is the original length. The relation between stress and strain in elastic materials is given by Hooke's law, which is sigma is equal to E times epsilon, where E is Young's modulus of the material. Pressure sensors convert this mechanical strain into measurable electrical quantities. Types of pressure sensors. Different sensing mechanisms are used to detect pressure variations. The most common pressure sensor technologies include piezoelectric sensors, strain gauge sensors, capacitive sensors, and piezoresistive sensors. For instance, the strain gauge sensors work by changing the resistance due to an applied pressure. So the applied pressure would change the resistance of a material due to that compression, decompression factor. So compression when you have a higher pressure, decompression when you have a release of pressure, a lower pressure. So it would change the resistance, thereby changing the current flowing through that resistance. In the same way, almost, the capacitive sensors would have the capacity value or capacitance changing due to the applied pressure. Why? Because when you have an increase of pressure, the distance between the two plates, two oppositely charged plates, positive and negative, would change, and that change of distance would change the capacitance, and this would be translated as a change of pressure. Now, the strain gauge sensors and capacitive sensors are passive, meaning that they depend on a current going through them from an external source, and the change of the current, the change of the current would be detected through the change of the capacity or the resistance, okay? But they are passive, they are not active. Unlike the piezoelectric sensors and piezoresistive sensors, for the piezoelectric, the change of the distance between two oppositely charged plates would induce a current, okay? It's like an actuator that would create a current, correct? And this current would be translated as a change of pressure. But they are active, meaning that they create their own current without an external source. For the piezoresistive sensors, also the resistance would change due to an external pressure being applied. So this is how they actually work. Again, the change of distance between the oppositely charged plates would translate as a change of capacitance, and also this change of capacitance and the change of the magnetic field would create an induced current. This is what would be noticed and detected as a change of pressure. So this is how they work in detail. Starting from the piezoelectric sensors. Piezoelectric pressure sensors operate based on the piezoelectric effect. Certain crystalline materials generate an electrical charge when subjected to mechanical stress, to mechanical deformation. Okay? Actually, the stress itself creates also a strain, and this strain causes an induced current. The generated electric charge is proportional to the applied force, given by Q is equal to dF, Q being the generated electrical charge, D is the piezoelectric coefficient, and F is the applied force. Based on this relationship, we can detect the amount of force being applied, and since we have the area on which the force is being applied, you can detect also the pressure. The corresponding voltage can be expressed as V is equal to Q divided by C, where C is the capacitance of the crystal that would change due to the applied pressure. Common piezoelectric materials include quartz, lead zirconate or zirconate titanate, PZT, and barium titanate or titanate. Advantages: very high sensitivity to pressure variation, excellent dynamic response, so they are very resilient and they are very sensitive. Okay, and they produce a high accuracy, suitable for high frequency pressure measurements when you need the response to be immediate. Otherwise, you would get inaccurate results and you would have a lag between the outputted value and the inputted parameter, physical parameter, which is in this case the pressure. Disadvantages: not suitable for static pressure measurements where you'd have a static pressure being applied, and requires charge amplifiers because the signal being produced is very, very low. It needs to be boosted by an amplifier. Strain gauge sensors. Strain gauge pressure sensors measure the deformation of a diaphragm caused by pressure. The deformation produces strain, meaning a change of length of a material, which is a resistive element, and this change of length would change the resistance as well. So the electrical resistance would change as a result for the applied pressure. The relationship between resistance variation and strain, which is the deformation amount, is given by delta R divided by R is equal to G times epsilon, epsilon being the strain, G is the gauge factor, delta R is the change in resistance or resistance excursion, differential of resistance, divided by the original resistance without any applied pressure. The gauge factor is defined as G is equal to delta R divided by R divided by epsilon, which is the strain. Typical values for G range between 2 and 5 for metallic strain gauges. Strain gauges are commonly arranged in a wheat-stone bridge configuration to increase sensitivity. So V0 is equal to Vs, okay, Vs being the supply voltage, multiplied, and V0 is the bridge output voltage. So V0 is equal to Vs multiplied by R3 divided by R3 plus R4 minus R2 divided by R1 plus R2. Different resistances mounted in a way that the equivalent resistance of them all is given by this relationship. Advantages: you have high accuracy, good linearity, so linear relationship between input and output is very favorable, suitable for static pressure measurement, which is an advantage, not available for piezoelectric type. Disadvantages: they are sensitive to temperature. So temperature sensitivity means that when you have a higher temperature, the diaphragm would expand on its own, even without a decrease of pressure, or it would contract, okay, become more constricted without an increase of pressure due to the drop in temperature values. So this is one of the disadvantages or shortcomings. Another is it requires signal conditioning or signal adaptation. Capacitive pressure sensors. Capacitive pressure sensors detect pressure by measuring changes in capacitance caused by diaphragm displacement. The capacitance between two plates is given by C is equal to epsilon times A. Epsilon here is the permittivity, not the strain. Okay, multiplied by A, which is the plate area, divided by D, which is the distance between plates. So C is equal to epsilon A divided by D. C is the capacitance in farad, epsilon is the permittivity of the dielectric medium, and A is the plate area, while D is the distance between the two plates. When pressure is applied, the diaphragm deflects, causing the distance D between the plates to change. This variation modifies the capacitance or the capacity value. So the capacitance variation can be approximated as delta C approximately equal to minus epsilon A divided by D squared times delta D, which is the change of distance. The distance change between the two plates is reflected as a change of capacity. This is what's happening. Advantages: high sensitivity for low pressure, which is much needed for many applications. Low power consumption, so they are not gluten for power, so to speak. And good resolution, meaning that even when you have a very slight change of pressure, this can be detected and represented by the system. Okay, so their sensitivity is high and the number of values that are represented is very large. Okay, so like the rate between the full scale values of pressure and the actual values that are detectable is a good rate. Disadvantages, on the other hand, they are sensitive to temperature and humidity change, which can affect the accuracy of the sensor. Plus, they require precise electronic circuits that can like precisely detect the changes, okay, without any noise being introduced to the system. Piezoresistive sensors. Piezoresistive pressure sensors rely on the variation of the electrical resistance. Actually, it is the resistivity that changes, which also reflects in a change of the resistance. The relationship between both is R, the resistance in ohm, is given by rho L divided by S, where rho is the resistivity, the inverse of conductivity, by the way, multiplied by L, which is the length of the resistor, divided by S, or the cross-sectional area of the resistance. This resistivity in semiconductor materials changes under mechanical stress. In semiconductor materials, this resistivity changes due to the deformation or strain of the crystal lattice. The resistance change is given by delta R divided by R is equal to pi sigma, where pi is the piezoresistive coefficient and sigma is the applied stress, which is force divided by area. Because semiconductor materials exhibit stronger piezoelectric effects than metals, these sensors have higher sensitivity. So you would have silicon-based piezoresistive sensors are widely used in automotive pressure sensors, biomedical devices, and MEMS sensors, which is the micro electromechanical system sensors. Absolute versus gauge pressure or gauge pressure. Pressure sensors may measure pressure relative to different reference levels. Absolute pressure is measured relative to a perfect vacuum. Okay, so absolute pressure is given by gauge pressure plus atmospheric pressure. P absolute is the absolute pressure is given by, okay, P gauge, which is gauge pressure plus atmospheric pressure, which would be the reference pressure, by the way. This is the same system used in aircrafts, by the way, to like indicate the altitude, like the altimeter and even the airspeed indicator. So you'd have the external pressure of the air compared to a closed compartment where you'd have the atmospheric reference pressure. Okay, so the differential of pressure would move the diaphragm in a way that it would create an electrical signal indicating the pressure value due to the change of the resistance, for example, or the capacitance, depending on the application or like the type of sensors being used for pressure indications. Absolute pressure sensors are used in applications such as barometric pressure measurement, altitude measurement within the aircraft, for example, and vacuum systems. By the way, the entire system that measures the airspeed, the vertical speed indicator, also the VSI within the aircraft, and the altitude indicator, not altitude indicator, altimeter, the technical name for that. This entire system is called the vacuum system. Now, the gauge pressure is the one used to measure the altitude, the airspeed, and all the different parameters related to aviation, for example. So gauge pressure is measured relative to atmospheric pressure. P gauge is equal to absolute pressure minus atmospheric pressure. This differential, we can get from it different other parameters such as the airspeed, such as the altitude, etc. Gauge pressure sensors are commonly used in hydraulic systems, pneumatic systems, and tire pressure monitoring. Pneumatic system, by the way, is the landing gear of the aircraft. This is part of the pneumatic system. And also you have the de-icing boots, which are like a rubber boot, rubber overlay on the leading edge of the airplane wing, which keeps on inflating and deflating in order to break any ice being formed on the wing. Because as you might know, or as we already know, honestly, if I'm referring to myself, that the ice can degrade the lifting capabilities of the aircraft and it increases the induced drag. So that would be an important application for it, and you need a sensor to detect whether it is inflating properly or if there's a leak in the pressure. Pressure transducers. A pressure transducer is a device that converts pressure into an electrical signal suitable for measurement, processing, or control. A typical pressure transducer system consists of a mechanical sensing element, such as diaphragm or membrane, a conversion element, which is a strain gauge, capacitive resistor, sensor, etc., and signal conditioning or adaptation for the signal done by an electronic board. The general transfer relation of a pressure transducer can be expressed as V output is equal to K times P, where K is the sensitivity constant of the sensor, multiplied by P, which is the applied pressure, and this would induce or generate a signal at the output having a voltage V out. That is the output voltage. Modern pressure transducers often integrate MEMS or micro electromechanical systems, DSP or digital signal processing, temperature compensation, and these integrated systems provide high precision, meaning that the same results remain repeatable. So it reproduces the same results given that the same conditions or external factors are available. Okay, given the same conditions, the same external environmental circumstances, they reproduce the same results, the same measurements. Stability, meaning that the system is stable, it doesn't fluctuate if the input does not vary or change. And reliability, for industrial and scientific applications, reliability means that the system is trustworthy and we can depend on it. Okay, it reproduces, like it can produce accurate results given that the circumstances are changing. The change of the output is also analogous and conforming to the change of the input. Now, concerning DSP or digital signal processing, this includes sampling of the analog signal. Then, after sampling, one average value is taken from each sample. After that, quantization, meaning each value is snapped into a scale of fixed values that can be coded into binary words that are ingestible by a computer system or a software. As for temperature compensation, we need to compensate for the overheating of a sensor, because for some sensors, they would be, like for this type of transducers, they would be prone to temperature change, and this would cause inaccurate outputted voltage. Okay, so the change of temperature would cause a change of the contraction or release of the diaphragm, for example, causing inaccurate voltage to be released, to be generated. So we need a compensation or a cooling to keep the temperature nominal. Going back to DSP, okay, to produce like a graph to make it more understandable. So let's say the signal is like this, okay? What the sampling does is that it multiplies this signal by a square signal. Usually it is a stream of pulses, okay? Now, this square signal has two values, 1 and 0. Each time you multiply by 1, you get the signal. Each time you multiply by 0, you clip the signal. Okay, so here you have 1, the signal would be like this. Then here you have 1, okay, here you have 1, so it is multiplying the signal. And whenever you multiply something by 1, this something that you're multiplying remains. But when you multiply by 0, the signal becomes 0. Okay? So here you have another, here you have another signal, then you have another sample. Okay? So this result in the following signal, and here you have a multiplier, by the way. So it becomes something like this, where everywhere the signal has been multiplied by the 0 value, it became clipped. Now, from this set of samples, we get one average value like this one. This is still part of sampling. Then you enter a quantizer. Quantization meaning that you have a scale from 0 to n values. Okay, now let's say the value here, okay, let's say something like this. So if the value falls between two values of the scales, okay, where is it the closest? Is it the closest here or the one above? Okay, so it would be snapped here, where it is the close the most. Okay, now after snapping these values, okay, then we have this quantizer, let's say 1, 2, 3, 4, okay, 5. Okay, for 5 values, how many bits do you need? So 2 to the power of n is equal to 5. At least you would need 3 bits, okay, because 2 to the power of 3 give us 8 values possible. For 5 values, okay, you need at least 3 bits. Why? Because 2 to the power of 2 give us 4 values. Okay, now how to code these values? So let's say 0, 0, 0 is value of 1. 0, 0, 1 is 2. 0, 1, 0, 3. 0, 1, 1, 4, etc. Okay, this is how it works. Now, chapter 5 or module 5, position and displacement sensors. Position and displacement sensors are used to measure the movement of an object relative to a reference position. These sensors are essential in many engineering systems such as robotics, industrial automation, aerospace control systems to detect the distance from a point to another, and precision manufacturing. Displacement refers to the change in position of an object along a linear or angular axis. It is generally denoted by x is equal to x of t minus x0, where x0 is the reference position and x of t is the current position, which is in respect of time variable t. Displacement sensors convert mechanical movement into an electrical signal, such as voltage, current, frequency, or digital pulses. Common types of displacement sensors include potentiometric sensors, which change resistance based on the change of position, linear variable differential transformers or LVDT, optical encoders, okay, that detect the position based on an optical signal, and capacitive displacement sensors, where the capacity changes based on the distance between the two plates, okay, where you'd have the magnetic field between two plates. One of them is moving, and of course, they are charged oppositely, and inductive displacement sensors, where the inductive current, the induced current would change or would indicate the displacement between two plates. Starting from potentiometric sensors. A potentiometric displacement sensor measures position using a variable resistor. The displacement of a mechanical slider along a resistive track changes the output voltage. The device consists of a resistive element, a movable contact wiper, two fixed terminals connected to a voltage source. When a voltage Vs is applied across the resistive element, the output voltage is proportional to the position of the wiper. If the resistive track length is L and the displacement of the wiper is X, so the output voltage becomes Vout is equal to Vs, which is the voltage applied across the resistive element, multiplied by X, indicating the displacement of the wiper, divided by L, which is the track length, the full length of the resistive material. where Vs again is the supply voltage, X is the displacement, and L is the total length of the resistive element. This is how it works. Thus, the output voltage varies linearly with displacement. The advantages: the relationship is linear, direct linear output, which makes it less complicated and more predictable, low cost, and simple construction. Disadvantages: it mechanically wears out due to contact and friction, limited lifespan, so it wears out quickly and dies out quickly, would require replacement more often than other types of detectors, and it is susceptible to noise. LVDT, or linear variable differential transformer. LVDT is a highly accurate inductive displacement sensor used for measuring small deviations or linear displacements. The LVDT consists of the following: one primary coil, two secondary coils, and a movable ferromagnetic core, which by moving, it would change the induced current. It would change the field value within this magnetic space. Now, this is a passive system which needs to be excited by an alternating voltage from outside. It should be an external signal. Vp of t, which is the voltage, is given by V0 sin omega t or sine omega t. The magnetic field produced by the primary coil induces voltages in the two secondary coils. When the core is centered, the induced voltage in the secondary coils are equal. Vs1 is equal to Vs2. As this differential changes, okay, you would know where is the position of the sensor. So the differential output is 0 only when you have the position is in the middle, okay, of the primary coil. So V out would be Vs1 minus Vs2 equal to 0 when the position is middle. When the core moves from the center position, the coupling between the primary and secondary coils change. So the output voltage becomes proportional to the displacement amount. V out is proportional to X, which is the displacement, the excursion from the center, where X is equal to displacement of the core. More precisely, V out is equal to Kx, where K is the sensitivity constant of the LVDT. Advantages: you have high accuracy at first, due to the fact that it depends on the change of the magnetic field. So it has a high sensitivity due to the fact that the magnetic field is so sensitive to the change of position of the middle conductor in relationship or in respect to the secondary conductors on both sides, correct? Of course, the one which is changing position is the primary conductor, primary coil. You have excellent linearity, so linear relationship between input and output, no mechanical contact, so it has a longer lifespan, and it can operate on the basis of long operational time. Disadvantages: it requires an excitation, meaning an external AC source, alternative current source, and it has more complex electronics. Optical encoders. Optical encoders measure displacement or angular position using light detection techniques, just like the LiDAR. So the light source is the one used to detect the position or the distance. It consists of a light source, LED or laser, a rotating or moving disc with slots, and photodetectors. Okay, so you would have a light going out, then coming in, and by measuring the time it took the light to travel this distance, then come back, this is how, because we already know the speed of light within the void or within the air, and by measuring the time it took the signal to go out and then return, we can measure accurately the distance from the sensor or the head, which has both the sender and receiver device, and the target, which might be a wall or an object. Okay, so you would need a light source, such as LED or laser, rotating or moving discs with slots, and photo detectors. Now, this is how it actually works. Of course, we represented the concept of the signal going out and then coming back in, and by measuring the time span it took for the signal to be transmitted and then received, we can assess the distance between the sender and receiver. But this is a concept. It's not necessarily always the case, meaning that the system is more complex than this simplified way of getting the distance from the sender to the target. Correct? Okay? It involves more than that. As the disk moves, the slots alternately block and allow light to reach the photo detector. It produces, by this motion, a sequence of pulses. The displacement can be determined by counting the number of pulses given by x equal n times delta x, where n is the number of detected pulses and delta x is the displacement per pulse. So by counting the number of pulses times the displacement, which is the distance between two consecutive pulses, you can get the distance from the sender to the obstacle, to the target. Now, to give a picture of how or what that would look like, let's say you have the sender here, and here is the detector, the photodiode. So, and here you have a train of pulses. I'm making it as simple as possible. Of course, they would not be as wide as this representation. So how many pulses are there? 1, 2, 3, 4, 5, 6. 6 multiplied by the distance, the displacement, or the distance separating two consecutive pulses. Let's say it is 0.5 centimeter. Correct? So that would be 3 centimeters. For angular encoders, theta, which is the angular position, is given by 2 pi times n, which is the number of pulses that are being detected, divided by the total number of pulses per revolution. So how many pulses you get per revolution, okay? And how many pulses are being detected at the moment. The difference between both would give us the angular position. As we see here in this representation, so you have a light source and different cavities. So how many pulses are we detecting at the output? This would give us the angle of rotation, okay, at a specific moment for that disk. So this is a moving disk with slits, light receiving elements here being captured, or a photodiode actually, and this is a signal converter that would convert the photoelectric signal into the light signal into an electric signal. This electric signal can be processed to detect the speed of rotation for that device, for that disk. Two main types of optical encoders exist. You have the incremental encoders and absolute encoders. Advantages: very high precision and resolution. Okay, the resolution means that even for the slightest angular changes, these angular changes are detected and represented. They are perceived, so the perception or sensitivity is high. And non-contact measurement, which means that no mechanical part would wear out. As for disadvantages, they are very sensitive to dust because they would block the light signal and contamination. Plus, they require precise alignment between the LED or the laser emitter and the photoreceptor. Capacitive displacement sensors. Capacitive sensors measure displacement by detecting changes in capacitance caused by variations in the distance between conductive plates. Of course, they are charged oppositely, one charged positively and the other negatively. The capacitance between two parallel plates is given by C is equal to epsilon A divided by D, where epsilon is here the permittivity of the dielectric or the medium, C is the capacitance, A is the plate area, and of course D is the distance between the plates. So the game is through measuring or detecting the change of distance between the plates, which would change the capacitance, and thereby would alter the current being received or detected, okay, that is coming out from the capacitor. If one plate moves due to displacement x, the distance becomes d is equal to d0 plus x. Thus, the capacitance becomes C is equal to epsilon A divided by d, which has become d0 plus x. For small displacements, delta C is approximately equal to minus epsilon A divided by d0 square times x. This change in capacitance can be measured using electronic circuits such as oscillators or bridge circuits. Mathematically speaking, how did we get this value down below? So delta C is equal to C2 after displacement minus C1, which is the original capacitance, equal to epsilon A divided by d0 plus x minus epsilon A divided by d0. Let's form a common denominator here, so it becomes d0 square plus d0 x. Then here you have d0 epsilon A minus d0 epsilon A minus minus x epsilon A, correct? Minus x epsilon A. So this annihilates. We are left with epsilon A times x, and here you have a minus, divided by d0 square plus d0 x. Okay, now d0x is negligible for small values of x, so we are left with this relationship, minus epsilon A divided by d0 square multiplied by x. Advantages: extremely high resolution, so it detects even the slightest changes of displacement or position, suitable for very small changes of distance or small displacements, no mechanical contact, so they won't wear out quickly, and they have a long span or time span for service, a long lifespan. Disadvantages: they are sensitive to environmental factors such as, for example, high temperature and other similar factors that can contribute to getting inaccurate values, and they have a limited measurement range, so they cannot detect a larger scope of values. Inductive displacement sensors. Inductive displacement sensors operate by measuring changes in inductance caused by the movement of a metallic target. This would be within a magnetic field, of course. The inductance would change. Why? Due to the change of the magnetic field intensity. And this inductance of a coil is given by L is equal to mu n square times A divided by lowercase l. L, lowercase l, would be the magnetic path length. L is the inductance value. Mu is the magnetic permeability. N is the number of turns, okay, within the coil. And finally, A is the cross-sectional area of the coil. So it is straightforward. When a ferromagnetic object approaches the coil, the magnetic permeability of the circuit changes, resulting in a variation of inductance. The inductance variation can be expressed as delta L is directly proportional to x, where x is the displacement amount. The inductance variation is then converted into a voltage signal using oscillators or bridge circuits. Advantages: robust and reliable, which means the value you get is trustworthy and dependable, suitable for harsh environments where you'd have high temperatures or humidity, for example. Non-contact measurement, so they have a long lifespan. Disadvantages: limited measurement distance or range, and they are sensitive to electromagnetic interference when you have an external electromagnetic field. It can affect the values being read by the computer system and the accuracy of the result, of the outputted result. Summary of displacement sensor characteristics. Different displacement sensing technologies offer different trade-offs between accuracy, range, cost, and environmental robustness or immunity. So you have potentiometric sensor, accuracy moderate, contact based, yes, and typical applications in industrial controls. LVDT, very high accuracy, no contact, so it has a longer lifespan. Typical applications, aerospace, precision measurement. Optical encoder, very high accuracy, no contact also for robotics and automation. Capacitive, extremely high accuracy, no contact for nano positioning. Inductive, high accuracy, no contact, and for industrial automation as well. These sensors are fundamental components of modern motion control and positioning systems. Chapter 6 or Module 6, Motion Sensors. Motion sensors are devices used to measure the movement of an object or system. These sensors detect parameters such as velocity, acceleration, tilt, angular motion, and orientation. Motion sensing is fundamental in many engineering systems, including robotics, aerospace navigation, automotive safety systems, and consumer electronics, such as the PlayStation joystick. Motion sensors operate based on principles from classical mechanics, particularly Newton's laws of motion. The fundamental relation governing motion is given by Newton's second law, which is F equal ma, or sigma F is equal to ma. The sum of all forces, the vectorial sum, is equal to the mass of the system multiplied by the acceleration. So F would be the applied force or the resulting force, which is the sum of all forces, equal to the mass of the object multiplied by the acceleration. Motion sensors typically measure velocity or acceleration and then derive other motion parameters through integration or differentiation. An example for that is the velocity is the derivative of the displacement or motion distance in respect of time, and the acceleration is the derivative of the velocity, which is the change, rate of change of velocity in respect of time, or second derivative of x, which is the distance in respect of time. Velocity sensors. Velocity sensors measure the rate of change of displacement with respect to time. So it is defined by v equal dx over dt, which is the derivative, first derivative of the distance in respect of time. V being velocity, x equal displacement, and t equal time. These sensors may operate using several physical principles such as electromagnetic induction, Doppler effect, which is the change of the wavelengths of a signal, light signal, due to the change of velocity in respect of the receiver, or optical detection. Electromagnetic velocity sensors. One common velocity sensor is the electromagnetic transducer, velocity transducer. It operates according to Faraday's law of electromagnetic induction, which is the creation or generation of a current due to the change of the magnetic field. The current or the voltage of the signal would be given by E equal to minus derivative of the magnetic field in respect of time. So E equal minus d phi over dt. Now, when a conductor moves within a magnetic field, an electromotive force, EMF, is generated, given by V is equal to BLV, where B is the magnetic field strength, L is the length of the conductor within the magnetic field, and V is the velocity of motion. Thus, the generated voltage is directly proportional to the velocity of the moving conductor. Doppler velocity sensors. Velocity can also be measured using the Doppler effect. This is actually the change of frequency due to the motion of the object moving or emitting the frequency. So for example, when you have when you're standing on the side of the road and you have a car that is playing music on a loudspeaker, as it approaches you, the frequency of the song, like the rhythm of the song, accelerates. It increases. And then when the car moves away from the spectator, which is you, on the side of the road, the music would start lagging. It means that the frequency, would feel that the rhythm and the frequency of the song lagging behind or decelerating, almost like a broken record. Okay, so it starts lagging behind, it starts decreasing in velocity and slowing down. But meanwhile, as the car approaches you, you feel that the song is accelerating. It's running faster, the rhythm is becoming faster. And this is basically the Doppler effect. Now, the Doppler shift is given by delta F, which is the change of frequency, is equal to V, 2 times the velocity of the object divided by lambda. So, by measuring the frequency shift, we can get the velocity of the moving object. Lambda, of course, is the wavelength of the emitted signal, the original wavelength. Doppler-based sensors are commonly used in radar, speed detection, and medical flow measurement, just like the radar at the airport. It uses the same concept. Accelerometers, these measure the acceleration of an object, as the name indicates, of course. Acceleration is defined as the rate of change of velocity in respect of time. So it is the derivative of the velocity parameter in respect of time, or A equal dv over dt. Acceleration sensors are typically based on the motion of a proof mass inside the sensor structure. So there would be a mass that is moving inside the sensor, and the rate of motion, it would be, for example, connected to a spring or something, how much it is deviating or it is stretching from the original position. That would indicate the change of speed, which is, in other words, the acceleration. Mass spring accelerometer model. A common accelerometer design uses a mass attached to a spring. When the device accelerates, the inertia of the mass produces a displacement relative to the sensor frame. So the force acting on the mass is given by F equal ma. According to Hooke's law, F is also equal to K times X, which is K being the spring constant and X is the displacement of the mass. So F equal X, A would be equal to Kx over m. This is how we get the acceleration. How much displacement we've gotten in reference to the original position or measurement frame. Again, combining both relations gives ma is equal to kx, because both are equal to f. Thus, the displacement is proportional to acceleration. X is equal to m divided by k times a. X is measurable, can then be measured using capacitive piezoresistive systems or optical techniques. And when we get X, we can derive A, which is the acceleration. Piezoelectric accelerometers. In piezoelectric accelerometers, the inertial force acting on a crystal generates an electric charge due to the shear stress being applied on the crystal material. This electric charge, of course, is proportional to the displacement and thus to the acceleration. Not the displacement, so to speak, the strain. And it is proportional to the acceleration that we want to measure. The generated charge is given by Q is equal to dF, where Q is the electric charge, D is the piezoelectric constant, dependent on the type of the crystal or material, and F being the applied force. Of course, we also know that force is equal to ma, so we can derive the acceleration from the force, which we have here, and the mass. So F is equal to ma, Q then is equal to dma. Corresponding voltage can then be obtained using V is equal to Q divided by C, or the ma divided by C, where C is the capacitance of the crystal. M is the mass of the crystal being moved, being sheared. Gyroscopes. Gyroscopes measure angular velocity and orientation. They are essential components in navigation systems, especially in aircraft stabilization systems and robotic motion control. Angular velocity is defined as omega is equal to the change of angle in respect of time. So it is how fast an object is rotating in respect of time, or the rate of change of angle in respect of the time factor. So omega is the angular velocity and theta is the angular displacement. Mechanical gyroscopes. Traditional gyroscopes consist of a spinning rotor mounted on gimbals. Due to conservation of angular momentum, the rotor maintains its orientation in space. So let's say you have, for example, the attitude indicator of the airplane. You would have a rotor, a gyroscope rotating in the horizontal direction. So even when the aircraft rotates right or banks right or left, the rotor, due to the conservation of angular momentum, would remain stable in a horizontal orientation. So it is still spinning horizontally while the aircraft is pending, or like it is banking left or right. So that would accurately indicate the bank angle. How much is the inclination between the plane of the airframe within the way, or along with the wings, and the horizon? That would be indicating the bank angle, or in other words, the roll angle of the aircraft. The angular momentum is given by L is equal to I omega, where L is the angular momentum, I is the moment of inertia, and omega is the angular velocity. The torque applied to a rotating body produces a change in the angular momentum. This is given by tau is equal to dl over dt, the derivative of the momentum, angular momentum, in respect of time. Vibratory gyroscopes. Modern gyroscopes often rely on vibrating structures and the Coriolis effect, which means that when something is rotating, the matter around that thing would go sideways, would be pulled sideways. So when a vibrating mass moves within a rotating frame, a Coriolis force appears, which pulls that mass sideways. Okay, so F of C, which is the Coriolis force, is given by 2m multiplied by V times W, which is, by the way, a vectorial product between two vectors. M is the mass, V is the velocity of vibrating mass, and W is the angular velocity. The Coriolis force causes a measurable displacement proportional to the angular velocity, a displacement of something vibrating on top of the rotating disk, or whatever that would be. MEMS motion sensors, or micro electromechanical systems. MEMS sensors are miniaturized devices that integrate mechanical sensing element with electronic circuits on a semiconductor chip. MEMS motion sensors include MEMS accelerometers, MEMS gyroscopes, and MEMS magnetometers. These sensors typically operate using capacitive sensing, or detecting the change of capacitance. For a capacitive MEMS accelerometer, the capacitance between electrodes changes as the proof mass moves. The capacitance value is given by C is equal to epsilon A divided by D, where epsilon is the dielectric permittivity, A is the area of the electrode area, and D is the distance between the two plates that are oppositely charged. Okay? When acceleration occurs, the displacement delta D changes the capacitance. Delta C is approximately equal to minus epsilon A divided by D squared delta D. So the change of distance, or the displacement, reflects in the change, or in a change of the capacitance value. This is how we get the motion change, okay? Electronic circuits convert this capacitance change into a measurable voltage. MEMS technology enables extremely small, low-cost, and low-power motion sensors. Applications of motion sensors. Motion sensors are widely used in modern technology, especially in smartphones. So smartphones contain multiple MEMS sensors, including accelerometers and gyroscopes. These sensors enable screen rotation detection, gesture recognition, gaming motion tracking, like when you are using your smartphone as a steering wheel in car chase or car racing game, and step counting. Aircraft navigation. Aircraft navigation systems use inertial measurement units, or IMUs, composed of accelerometers and gyroscopes. The position of the aircraft can be determined through inertial navigation by integrating acceleration over time. So V of t is equal to integral of A of t, and then the motion distance being traveled is equal to the integral of V of t dt. Robotics. Robotic systems use motion sensors to monitor position, orientation, and movement. Applications include robotic arm control, autonomous vehicle navigation, drone stabilization, and industrial automation. Motion sensors enable robots to perceive their environment and maintain stability during dynamic movements. Chapter or Module 7, Optical Sensors. Optical sensors are devices that convert incident light into an electrical signal, usually using a photoelectric diode. They are widely used in imaging systems, industrial automation, environmental monitoring, and scientific instrumentation. The operating principle of most optical sensors relies on the photoelectric effect, which converts the light signal, the solar energy or the light energy, into an electrical signal, in which photons incident on a semiconductor generate charge carriers. This is how it works. Optical sensors can measure different properties of light, such as intensity, wavelengths or frequency, in other words, position, and temporal variation. Common types of optical sensors include photodiodes, phototransistors, charged coupled device (CCD) sensors, complementary metal oxide semiconductor CMOS sensors. Let's start with photoelectric effect and sensor response. When light with photon energy E strikes a semiconductor material, electrons can be excited from the valence band to the conduction band if the photon energy exceeds a certain threshold. So if it exceeds the band gap energy, then the electron transiently moves from a lower energy band to a higher one. The photon energy is given by E is equal to h nu, where nu is the frequency of the electron of the wavelength, which is equal to hc over lambda. H is Planck's constant given by 6.626 times 10 to the power minus 34 joule per second. Nu is the frequency of the light, and c is the speed of light, which is 3 times 10 to the power of 8 meter per second. And of course, lambda is the wavelength. The generated photocurrent in many optical sensors is proportional to the incident optical power. I is equal to R times P, where I is the photocurrent in amperes, P is the incident power of the optical signal in watts, and R is the responsivity, which is 8 by W, ampere per watt. Now, to elaborate on how the system actually works, or how rather the phenomena works. So you would have an atom here, for example, where there's a nucleus made of protons and neutrons. Let's say the protons are the red balls here, which are the positively charged particles separated by neutrons so that they wouldn't fly off, due to the fact that equivalent charges would be repulsive against each other, would push each other away, and they are surrounded by electrons, correct? The electron is usually located at a certain distance on a specific energy band, in respect to the nucleus, meaning that based on its energy level, it would be located at a specific orbit far away of a certain distance from the nucleus. This distance and this orbit depends on the energy level on this electron or at this electron. So when you increase that energy level, this electron would be pushed with a higher momentum, so to speak. So the velocity would increase and it would escape to a higher orbit, just like when you increase the velocity of a satellite around a planet. This increase of velocity would make the satellite escape to a higher orbit, far away from, even like much further from the nucleus, which is the center of rotation. Okay, the same concept applies here. When an electron is excited by an external photon, and by the way, the photon is actually an energy carrying particle. It is a force carrying subatomic particle. This is what photons represent. So the photon, once it hits the electron, it gets it excited, increasing its energy level. So once it crosses the threshold of the energy band that the electron is originally positioned at, this electron escapes to a higher orbit. Now, as you keep increasing the excitation of the electron or increasing its received energy, it would keep escaping to even higher orbits until it completely had crossed or trespassed above all the energy levels around the nucleus within the atom. So this makes the electron eventually escape from the atom, becoming a free electron and creating a flow, an electronic flow, which is actually the current, which is what we call a current. So these charges, negative charges that are released, form a flow of current having a value in amperes. The responsivity depends on the quantum efficiency of the sensor and the wavelengths of the incident light. So R, which is the responsivity, is equal to eta multiplied by Q divided by H nu. H is Planck's constant, nu is the frequency, Q is the charge, and eta is the quantum efficiency. Or equivalently, it is given by R eta Q divided by H multiplied by lambda over C, which is the inverse of nu. Okay, lambda over C is actually the inverse of the frequency nu, where eta is the quantum efficiency and Q is the electron charge given by 1.602 times 10 to the power of minus 19 coulombs. Photodiodes. A photodiode is a semiconductor device that converts light into current using a reverse biased PN junction. Operating principle. When photons strike the depletion region of the diode, electron-hole pairs are generated. The internal electric field separates these carriers, producing a current proportional to the incident light intensity. The total current of a photodiode can be expressed as I is equal to ID minus IPH, where ID is the diode current and IPH is the photocurrent generated by the light itself. The diode current follows the Shockley equation given by ID is equal to IS, which is the saturation current, multiplied by exponential of QV divided by KT minus 1. Okay, let us break it down. So ID is the actual current being measured for the diode. IS is the saturation current, because each diode has a current of saturation when it becomes like a short circuit, multiplied by E, which is the exponential of QV divided by KT. Q is the charge, V is the voltage for the diode, divided by KT, which is Boltzmann constant, times the absolute temperature. Q, I think, is the charge of one electron. Modes of operation. You have photovoltaic mode, zero bias. By the way, the same system is in the solar energy panels. and photoconductive mode, which is a reverse bias system. Reverse bias operation provides faster response and wider dynamic range, so wider range of values that can be detected, so to speak. The advantages: fast response time, high sensitivity, and good linearity. Now let's explore the differences between the photovoltaic mode and the photoconductive mode, starting from the bias voltage. For the first one, it is zero bias, so it is unbiased by any external source, unlike the photoconductive mode, where you have a reverse bias from an external voltage, which has the advantage to widen the depletion mode and thus decreasing the capacitance of the photodiode, allowing the sensor to be much responsive or to respond much faster to light changes. Now, of course, this comes at an expense of increasing the dark current. Dark current means the existence of a current when there's no actual light, due to the sudden fluctuations, the very swift fluctuations between different pulses. Okay, so this would create like a twilight zone where you would have a current called dark current when there's no actually any light. The speed: for the photovoltaic mode, you have a slower speed and high capacitance. And by the way, it can process signals at a lower rate. Now, on the other hand, it has an advantage of detecting signals of much fainter light intensity, but it cannot process high pace signals, okay, like high speed signals that are at a much higher frequencies. Meanwhile, for the photoconductive mode, it has a lower capacitance, much faster, allowing it to process signals at a much higher rate. Okay, it can detect signals at a much faster pace. In another word, it can respond to light changes much faster, which is, by the way, in the nanosecond range. Now, dark current. For the photovoltaic mode, it has minimal to none dark current. Dark current means the existence or the presence of a current when there is no actual light signal, which is in a twilight zone between the transition of two light signals that are very close to each other. Okay, so since it is minimal, it allows the detection of much fainter light signals. Meanwhile, for the photoconductive mode, it has a much higher dark current, introducing much electronic noise to the detector. This is the drawback for such a mode. Linearity: it is good, but can be non-linear, which makes it non-predictable in some stages. Meanwhile, for the photoconductive mode, it is excellently linear, so to speak, so it is much stable and much predictable. For the primary use, the photovoltaic mode is used for low light, low frequency type of signals, okay? Low frequency sensing. Meanwhile, for the photoconductive mode, it is used in fiber optics transmissions, okay? So for high-speed data processing and high-speed optical signals, where you would have an application in DWDM, or dense wavelength division multiplexing, for optical transmission. Phototransistors: a phototransistor is similar to a photodiode, but provides internal current amplification. So, operating principle: light generates a base current that is amplified by the transistor's current gain beta. The collector current is approximately IC, okay, is equal to beta IPH, where IC is the collector current, IPH is the photocurrent generated at the base, and beta is the current gain of the transistor. Looking at this illustration to the right, so this is the collector current that we're talking about, this is the base, and this is the emitter. So the collector current is approximately IC is equal to beta IPH, beta being the current gain of the transistor, and IPH is the photocurrent generated at the base, which is here, at this point. Characteristics: compared to photodiodes, they have higher sensitivity, lower speed, and greater output signal. Phototransistors are commonly used in object detection, optical switches, and infrared receivers. CCD sensors, which are the charge-coupled devices. CCD sensors are widely used in digital imaging systems. The structure: a CCD consists of an array of light-sensitive capacitors such as pixels. Each pixel accumulates charge proportional to the incident light. The generated charge is given by Q is equal to eta pt over h nu Q. Lowercase q is the charge of one electron, T is the integration time, P is the light power, eta is the charging efficiency, so to speak, or conversion efficiency from light to charge, divided, which is, by the way, subject to the type of material that we are using. H is Planck's constant, and U is the light frequency, with Q, of course, being the collected charge. Charge transfer mechanism: after exposure, the stored charges are shifted sequentially through the array and read at the output amplifier. The charge transfer efficiency, CTE, is an important parameter. CTE is equal to Q out divided by Q in, which is how much of the charge is at the output coming from the input. Values close to 1 indicate efficient transfer. The advantages: high image quality, low noise factor, and high uniformity. Disadvantages: higher power consumption because they are more sophisticated, slower readout, so it's not like an instant readout, there's a lag between the input and the reaction to it to produce the output, and a more complex fabrication, so the manufacturing would be more costly. CMOS sensors. CMOS stands for complementary metal oxide semiconductor. This image sensor integrates photodetectors and signal processing circuits on the same microchip. Pixel structure: each pixel typically contains a photodiode, an amplifier to amplify the signal being received by the photodiode because it would be a very weak reception, a reset transistor to refresh the reading so as to allow a new updated reading of the light signal without any contamination or distortion, and finally, select transistor. The voltage generated by the photodiode is approximately V out is equal to Q divided by C, where Q is the accumulated charge and C is the pixel capacitance. Advantages: low power consumption, also, if I may add, a much simpler structure, less requirements for manufacturing, but also it is less sophisticated, and we're going to see why. So it has also high integration capability, faster readout, so it's not as sophisticated, but it's faster in operation, and it has a lower cost because the manufacturing is much simpler than the CCD. However, there are disadvantages in return. Higher noise compared to CCD historically, and also pixel-to-pixel variability, which means that the reading is not consistent from one pixel to the next. However, modern CMOS sensors have significantly improved and are now used in large scale within most imaging systems. Applications of optical sensors. Optical sensors are essential components in many technological systems. Let's start with the cameras. Digital cameras use CCD or CMOS sensors to capture images. Each pixel converts light intensity into an electrical signal, which is then digitized and processed, becoming a digital sequence of bits. The brightness captured by each pixel depends on the integration time and incident optical power. Signal is proportional to P times C, which is integration time times the optical power of the signal being received, the light signal. Light meters. Light meters measure illumination levels in photography and lighting design. Photodiodes are commonly used due to their linear response to light intensity, so they are more predictable. Illuminance E is related to optical power by E is equal to P divided by A, where P is the optical power in watts and A is the sensor area. So the illuminance is that proportion, power divided by sensor area. Optical sensors are used for object detection and automation in industrial environments. Typical systems include optical encoders, barcode scanners, for example, conveyor belt object detection, and safety light curtains. In many cases, the system detects a change in received optical power, which is delta I is equal to R times delta P, the received optical power times the change of the power intensity. Okay, this change triggers control electronics to perform actions such as stopping machinery or counting objects. R, by the way, would be like the resistance, and delta P is the change or the variability of the optical power, I being the change in light intensity. Finally, optical sensors convert light energy into electrical signals using semiconductor physics. Photodiodes and phototransistors are commonly used for light detection, while CCD and CMOS sensors are widely used for imaging applications. Their performance is characterized by parameters such as responsivity, quantum efficiency, noise, and dynamic range. Chapter or Module 8, Magnetic Sensors. Magnetic sensors are devices capable of detecting and measuring the magnetic fields. They convert magnetic field variations into electrical signals. An example for that would be the autoinduction. That can be processed by electronic systems. So these electrical signals can be processed by electronic systems and they would reflect the change in the magnetic field. These sensors are widely used in industrial automation, navigation systems, automotive electronics, robotics, and scientific instrumentation. Magnetic sensing technologies rely on different physical principles such as the Hall effect, magnetoresistance, or the change of resistance due to the change of the magnetic field, and magnetic flux detection. Common types of magnetic sensors include Hall effect sensors, magnetoresistive sensors, and flux gate sensors. Magnetic sensors measure the magnetic flux density, which is B, typically expressed in Tesla. Fundamental principles of magnetic field measurement. When a charged particle moves through a magnetic field, it experiences a force known as Lorentz force. This force is expressed by F is equal to Q multiplied by V times B. And this is a vector multiplication between V being the velocity of the charge, because it might be in X, Y, Z planes, times B, which is the magnetic flux density. Okay, with Q is the charge of the electron, okay, the electric charge. This interaction between moving charges or charge carriers and magnetic fields is the physical basis of many magnetic sensors. This is how they work. Hall effect sensors or Hall effect principle. The Hall effect occurs when a current carrying conductor or semiconductor is placed in a magnetic field perpendicular to the direction of the current flow. So if the magnetic field is like this and the current is like this, 90 degrees apart from each other, this is what creates the Hall effect. The magnetic field causes charge carriers to be deflected due to the Lorentz force, creating a measurable voltage across the conductor. Current direction I, magnetic field B, 90 degrees opposite from each other, and the resulting voltage would become VH. This voltage is called the Hall voltage due to the fact that the current is crossing a magnetic field that is 90 degrees apart from it. Hall effect relation, the Hall voltage, which is created due to the fact that a current is crossing against a magnetic field at an angle of 90 degrees, is given by VH is equal to IB divided by NQT. With VH is the Hall voltage, I is the current flowing through the sensor, B is the magnetic field or flux density, in Tesla. N is the charge carrier density, number of charges. Q is the electron charge, which is 1.6 times 10 to the power minus 19 coulombs. And T is the thickness of the conductor. The sensitivity of the Hall sensor depends on the material properties and geometry. Hall coefficient. The Hall coefficient is defined as RH is equal to 1 divided by NQ. Thus, the Hall voltage can also be written as VH is equal to RH times IB divided by T. The materials with low carrier density, such as semiconductors, produce large Hall voltages and are therefore commonly used in Hall sensors. Okay? In other words, such materials with low carrier density can cover a wider range of fluctuations in the magnetic field and therefore would be more effective in the usage of the application where you need to detect different changes of magnetic fields even at lower and higher ranges. Hall sensor structure. A typical Hall sensor consists of semiconductor Hall plate, current source, voltage measurement electrodes, and signal conditioning circuitry. Types of Hall sensors: linear Hall sensors, analog output, digital Hall switches, and latching Hall sensors. Advantages: contactless measurement, so they would become more integrable than other types of sensor within the environment because there is no direct contact between them and the measurement area, so to speak. Longer lifetime or lifespan, good reliability, so they are trustworthy and accurate, and low cost of fabrication or manufacturing. Magnetoresistance sensors. How does the principle work? Magnetoresistance refers to the change in electrical resistance of a material when exposed to a magnetic field. The resistance variation can be expressed as R of B is equal to R0, which is the reference resistance without magnetic field, plus delta RB, which is the change in resistance due to magnetic field presence. The relative change in resistance is often expressed as delta R divided by R0. Magnetoresistive sensors exploit this effect to measure magnetic fields with high resistivity or sensitivity. Types of magnetoresistive effects. Several types of magnetoresistance are used in sensors. You have the AMR or anisotropic magnetoresistance, giant magnetoresistance GMR, and tunnel magnetoresistance TMR. Let's start with the anisotropic magnetoresistance. In AMR sensors, resistance depends on the angle between the electrical current and the magnetized environment or the magnetization direction, the direction vector of the magnetic field. So R is equal to R resistance when current is perpendicular plus resistance when the current is parallel to the magnetic field minus R perpendicular multiplied by cosine square theta, where theta is the angle between the current and the magnetic field. Giant magnetoresistance or GMR. GMR occurs in multilayer thin films composed of alternating bands, ferromagnetic and non-magnetic layers. The resistance depends on the relative orientation of magnetic layers. Parallel magnetization, you'd have a low resistance. Anti-parallel magnetization, you'd get a higher resistance. This effect is widely used in magnetic reed heads and precision sensors. Now, concerning how it works, a spin-dependent electron would scatter in thin layered materials. This is what would cause the change or the fluctuation of resistance within the sensor. This is how basically it relies on a quantum principle to measure the change or fluctuation of the magnetic field. So basically, for parallel magnetization, the electron flow would be in the same direction of the layers, okay, the magnetic, non-magnetic layers, so the current would flow much easily. Meanwhile, for the anti-parallel magnetization, you would have a higher resistance due to an increase of the electron scattering within the layers. Advantages of magnetoresistive sensors: high sensitivity, capability to detect very small magnetic fields, good temperature stability even when the temperature changes. They are still stable and suitable for miniaturization, which means integration with smaller electronic boards. Flux gate sensors, which is the third type. Operating principle: flux gate sensors are highly sensitive magnetic field sensors used for measuring very weak magnetic fields. They operate based on the periodic saturation of a ferromagnetic core. A typical flux gate sensor consists of a ferromagnetic core, an excitation coil, and a sensing coil. Magnetic core excitation: an alternating current flows through the excitation coil, given by I of t is equal to I0 sine omega t. This current produces a magnetic field that periodically drives the core into magnetic saturation. The magnetic flux inside the core is given by B is equal to mu H, where mu is the permeability, magnetic permeability, of course, and H is the magnetic field strength. Of course, B is the magnetic flux density. So I of t, which is the current at time t, is given by I0, saturation current, multiplied by sine omega t. Omega, of course, is the pulse, which is equal to 2 pi f, with f being the frequency. Detection of external magnetic field. If an external magnetic field Bx is present, it distorts the symmetry of the magnetic saturation cycle. This produces even harmonics in the induced voltage of the sensing coil. The induced voltage follows Faraday's law, given by V is equal to minus N d phi, which is the derivative of phi, magnetic flux, divided by dt, okay, in respect of time. N is the number of coil turns, sphere in French. By detecting the harmonic components, the external magnetic field can be measured with very high precision. Characteristics: extremely high sensitivity, ability to measure weak magnetic fields, and excellent stability. Typical measurement range: flux gate sensors can measure magnetic fields as low as 10 to the power of minus 12 Tesla. This makes them suitable for geophysical and space applications. An example for that came to my mind even before getting to this point is astronomy applications. Applications of magnetic sensors. Magnetic sensors are used in a wide variety of industrial and commercial applications. Position sensing. Magnetic sensors can detect the position of objects using permanent magnets or magnetic patterns. This is how they can assess the distance to an object. Typical examples include linear position sensors, rotary encoders, and proximity switches. The position is often inferred from variations in the magnetic field. B of x is equal to f of x, where x represents the position. Motor control. Due to the fact that the magnetic field changes with the rotation of a motor or a generator, magnetic sensors are widely used in electric motor control systems. Applications include rotor position detection, speed measurement, speed of rotation, and commutation of brushless DC motors. The rotational speed can be calculated from detected magnetic pulses, exactly, given by omega is equal to 2 pi n divided by t, where n is the number of detected pulses and t is the measurement time. This is how you can get the angular momentum from which we can derive the speed of rotation. Automotive systems. Magnetic sensors are essential components in modern vehicles. Typical automotive applications include the ABS or anti-lock braking system, crankshaft position sensing of the motor of the engine, wheel speed sensing, also sensing the speed of the wheel in a vehicle, steering angle detection, and throttle position sensing when it comes to airplanes. For example, the wheel speed sensor detects variations in magnetic flux as a toothed wheel rotates. F is equal to N, which is the number of t's, multiplied by omega, the angular velocity, divided by 2 pi. F would be the pulse frequency. So knowing the number of t's within a wheel and getting or detecting the pulse frequency, we can get the angular velocity, which is what we would be after by using this type of sensors. Finally, magnetic sensors play an essential role in modern electronic systems. Hall effect sensors provide simple and robust magnetic field detection, while magneto-sensitive or magneto-resistive sensors offer higher sensitivity and precision, while flux gate sensors allow the measurement of extremely weak magnetic fields, especially in aerospace or space applications like astronomy or geological applications. These technologies are widely applied in industrial automation, motor control, automotive systems, navigation, and scientific instrumentation. Chapter 9: Chemical and Gas Sensors. Chemical and gas sensors are devices designed to detect and measure the concentration of chemical substances in gases or liquids. These sensors convert chemical information such as concentration, reaction rate into measurable electrical signals. Chemical sensing is essential in many fields, including environmental monitoring, industrial safety, healthcare, and process control. Depending on the sensing principle, chemical sensors may measure physical quantities such as electrical current, resistance, optical absorption, or potential changes resulting from chemical interactions. The most common types of gas sensors include electrochemical sensors, semiconductor gas sensors, which are based on the same principle of capacitors, and infrared gas detectors. These sensors differ in terms of detection mechanisms, sensitivity, selectivity, and response time. Electrochemical sensors. Operating principle. Electrochemical gas sensors detect gases through chemical reactions occurring at electrodes. When the target gas interacts with an electrode surface, oxidation or reduction reactions occur, generating an electrical signal which is proportional to the concentration of the gas or gas concentration. A typical electrochemical sensor consists of working electrode, a counter electrode, reference electrode, electrolyte, and gas permeable membrane, which allows the gas to enter in for detection. The target gas diffuses through the membrane and reacts at the working electrode. Electrochemical reactions. The reactions occurring in the sensor can generally be written as gas plus Ne minus, which is the electron times the number of the electrons, would give us the reaction products, or the gas would, so to speak, produce without being added with an electron or triggered by an electron, products plus Ne minus, with N being the number of transferred electrons and E minus is the electrons participating in the redox reaction. For example, the oxidation of carbon monoxide in a CO sensor can be expressed as CO plus H2O would give us CO2, carbon dioxide plus 2H plus, which is 2 hydrogen particles, 2 protons basically, plus 2 E minus or 2 electrons. Sensor current. The electrical current generated is proportional to the rate of the electrochemical reaction and therefore to the gas concentration. So they reflect each other. The gas concentration would reflect the flow or the flux of electrons being introduced within the current and thus the current intensity. According to Faraday's law, the generated current is given by I is equal to Nf dN over dt, derivative of n in respect of time, where I is the sensor current, which we are after, n is the number of electrons per reaction, F is Faraday constant, which is 96485 coulombs per mole, and dN over dt is the rate of chemical reactions. This is the factor that you would be looking for. If diffusion limits the reaction, the current becomes proportional to gas concentration. So I is equal to Kc, where C is the gas concentration and K would be the sensor sensitivity constant. Advantages: you have high sensitivity, good selectivity, low power consumption, and linear response, which is very good. Typical detectable gases are carbon monoxide, CO, oxygen, hydrogen sulfide, H2S, and nitrogen dioxide, NO2. Semiconductor gas sensors. Operating principle. Semiconductor gas sensors operate based on the change in electrical conductivity of a semiconductor material when exposed to specific gases. The most commonly used sensing materials are metal oxides such as tin oxide, SnO2, zinc oxide, ZnO, and titanium dioxide or TiO2. These materials are typically heated to temperatures between 200 degrees Celsius and 400 to activate surface reactions. Here we spot a weak point or a weakness with this type of sensors, which is the need for an external power source in order to provide the heating, because they need to be heated to a high temperature so that they can become effective in detecting these different types of gases. So, without an external power source, they are irrelevant. Surface reaction mechanism. In clean air, oxygen molecules adsorb onto the semiconductor surface and capture electrons. So O2 plus E minus give us O2 minus. This process creates a depletion layer and increases the sensitivity or the sensor resistance. When a reducing gas such as CO is present, it reacts with the absorbed oxygen. So it gives us CO plus O minus, gives us CO2 plus 1 electron. This reaction releases electrons back into the conduction band, reducing the resistance. So this is how we can get the difference of concentration between oxygen versus the CO. Resistance change. The sensor output is typically the change in resistance given by R is equal to rho L divided by A, where rho is the resistivity, L is the length of the resistance, and A is the cross-sectional area. So rho is resistivity, L is the length of the sensing element in this case, and A is the cross-sectional area. The sensor response is often expressed as S equal R air divided by R gas, or S is equal to R gas divided by R air, resistance of the air, depending on the sensor type. Advantages: low cost, long operational lifetime, simple construction, and suitable for detecting combustible gases. Disadvantages: high power consumption due to the heater, as we mentioned before, limited selectivity, and sensitivity to humidity. So humidity becomes a noise factor, introduces a noise factor, creating an excursion, so to speak, or a deviation between the accurate supposed value and the presented value that would be displayed. As for selectivity, here we are referring to the types of gases that can be detected. So we have a limited range for the detection. Infrared gas detectors. Operating principle: infrared or IR gas detectors operate based on the absorption of the infrared radiation by gas molecules. Many gases absorb specific wavelengths of infrared light corresponding to their molecular vibrational modes. When infrared radiation passes through a gas sample, part of the radiation is absorbed. The amount of absorbed radiation is related to the gas concentration. An example for that phenomena is the fact that methane absorbs most of the white light spectrum but radiates back the green and the blue lights, the green and the blue wavelengths. This is how we recognize for specific gas planets that they are concentrated with methane, such as, I'm trying to remember, I think, no, it wasn't Uranus, perhaps Jupiter, okay, I'm not sure. These, I cannot recall exactly, but you have 2 or 3 planets that are concentrated with methane. And this is how we identified that, due to the fact that their colors, the color of the atmosphere is between light green, or actually, yeah, cyanic green and blue. Beer-Lambert law. The relationship between absorption and concentration is described by the Beer-Lambert law, given by I is equal to I0 exponential minus alpha CL, where I0 is the incident light intensity, I is the transmitted light intensity, alpha is the absorption coefficient, C is the gas concentration, and L is the optical length, optical path length, where you have like the presence or the thickness of the gas that's being detected. So again, I is the light that is being emitted or that passes through the gas versus I0, which is the light that is inserted. Now, the absorbance can also be expressed as A is equal to ln I0 divided by I is equal to alpha CL. Sensor components. An infrared gas detector typically includes infrared light source, optical filter, gas measurement chamber, and the length of this chamber is the L variable within the formula that we've observed previously. Infrared detector, which is the captor or the sensor, and signal processing electronics. Advantages: high selectivity, long-term stability, no chemical consumption, and suitable for continuous monitoring. Typical detectable gases, you have carbon dioxide, CO2, methane, CH4, which we've mentioned before, hydrocarbons, and refrigerant gases, such as the nitrogen. Going once again over the advantages to explain them further in a more elaborate way, we start with high selectivity and what it means. It means that this type of sensors, which is the infrared sensor, can detect a much larger range or a wider diversity of gases that can be detected or perceived by this type of sensors. Okay, so it can detect more gases than the former sensor types. Second, long-term stability, so it remains stable and can serve for a longer period of time, okay, with a longer lifespan, should I add, given the fact that this type of sensors does not have a direct contact with the gases, with the environment, so to speak, okay? So it's not very prone to being affected by the gases it is detecting. Third, no chemical consumption, so there is no direct chemical interaction between the gases and the sensor itself, which gives it, a longer stability and a longer lifespan. And fourth, suitable for continuous monitoring, which means that the refresh rate is great. It updates, it doesn't retain residual gases, which means that when the gas concentration or type changes, so does the detection and so does like the output. Okay, so there are no residuals that would affect the accuracy of the results being outputted by this type of sensors. Applications of chemical and gas sensors. Chemical and gas sensors play a critical role in many applications where monitoring gas concentration is necessary for safety, for example, environmental protection or health diagnosis or diagnostics. Environmental monitoring, gas sensors are widely used to measure atmospheric pollutants and greenhouse gases. Typically monitored gases include carbon dioxide, CO2, nitrogen oxides, NOx, sulfur dioxide, SO2, and ozone, O3. Air quality indices are often derived from concentration measurements. AQI is equal to FCI, where CI represents the concentration of pollutant I. Industrial safety. Gas sensors are essential for detecting hazardous gases in industrial environments, such as factories, mines, and chemical plants. Typical safety applications include detection of toxic gases, or flammable combustible gases, leak detection systems, and confined space monitoring. So one example would be detecting the oxygen concentration within a closed cabin, such as the onboard, cabin within the airplane. The risk level can be estimated by comparing measured concentration to threshold values. Risk is equal to C divided by C limit, where C is the measured concentration and C limit would be the safety exposure limit. So when C is 0, there would be no risk at all. When C becomes close to C limit, so you get 90%, 100%, which means C over C limit is 100% risk. Medical diagnostics. Chemical sensors are increasingly used in medical diagnostics for monitoring physiological gases. Examples include oxygen sensors in ventilators, breath analyzers to analyze the amount of CO2 that's coming out of the breath, blood gas analyzers, glucose sensors. For example, oxygen partial pressure measurement is often described by PO2 is equal to Ki, where PO2 is the oxygen partial pressure, I is the measured sensor current, and K is the calibration constant. Finally, chemical and gas sensors enable the detection and measurement of chemical substances through electrical, resistive, or optical signals. Electrochemical sensors rely on redox reactions. Semiconductor sensors detect changes in conductivity, and infrared detectors measure the optical absorption for the infrared signal. These technologies are widely applied in environmental monitoring, industrial safety systems, and modern medical diagnostics. Chapter or Module 10, Signal Conditioning for Sensors. Sensors often produce electrical signals that are very small, noisy, or incompatible with digital processing systems. Signal conditioning refers to the set of techniques used to transform raw sensor signals into a form suitable for measurement, that is, more detectable, processing, and control. Typical signal conditioning operations include amplification, filtering to remove the noise from the signal, noise reduction, another part of that, analog to digital conversion or ADC, and bridge circuit processing. Signal conditioning circuits are essential for improving measurement accuracy, increasing signal strength, and reducing unwanted disturbances. Amplification. Purpose of amplification: many sensors produce very small output signals, often in the range of microvolts or millivolts. So amplifiers need to increase the amplitude of these signals to levels suitable for processing by an electronic circuit or a computer. Also, this is required for analog to digital conversion. Amplification improves signal resolution, so it becomes more pronounced, measurement accuracy, and compatibility with electronic systems that would have a minimum threshold required for sensitivity for reception and processing of the signal. Operational amplifiers. Operational amplifiers or op-amps are widely used for sensor signal amplification. An op-amp can be configured in several ways depending on the application. The general voltage gain of an amplifier is defined as AV is equal to Vout divided by Vin. So it is the rate of change between the output voltage and the input voltage, where Vout is the output voltage and Vin is the one for the input. Non-inverting amplifier. In such type of amplifiers, the input signal is applied to the non-inverting terminal of the op-amp. The gain is given by AV is equal to 1 plus RF divided by RG, where RF is equal to feedback resistor and RG is the ground resistor. Thus, the output voltage becomes Vout is equal to 1 plus RF divided by RG times Vin. This is how this type of op-amps work. You have the input voltage being inserted in one of the inputs of the transistor, which is the op-amp circuit. Now, Vout, which is the output voltage, a part of it, we take it back and reinsert it in a retroaction behavior or in a retroactive architecture. We place it back in the second input of the transistor. Okay? Again, this is called retroaction, and this is where the term feedback comes from. So, a part of the output voltage is fed back into the second input. This is the resistor for feedback, which is R2 here in this graph, and it is RF within this equation or resistance of feedback feedback stage, and R1 is the ground resistor, which is RG. So what we get is Vout is equal to 1 plus RF, the feedback resistor, which is R2, divided by RG, the ground resistor, which is R1 here in this illustration, multiplied by V at the input. This retroactive behavior is what produces the amplification effect in this type of amplifiers. Instrumentation amplifiers for many sensor applications, such as strain gauges or pressure sensors, instrumentation amplifiers are used due to their high input impedance and excellent common mode rejection. The impedance, by the way, is another term for resistance, except the difference is the impedance has both real and imaginary parts. It is a complex number. The gain of a typical instrumentation amplifier is given by AV is equal to 1 plus 2R divided by RG, where RG is the gain setting resistor. Again, another reminder, these types of amplifiers are characterized by a high input impedance, so a high resistance, which would reject the common mode of the signal power. Filtering, purpose of filtering, at first, it removes unwanted frequency components from sensor signals, such as noise harmonics, noise components of the frequency, environmental noise, electromagnetic interference from outside, and power line disturbances, which can introduce unwanted signals, unwanted frequencies within the main signal. Filters allow specific frequency ranges to pass while attenuating others. So you have different types of filters, such as low-pass filters, high-pass filters, band-pass, and notch filters. So what are the different applications for the filters mentioned or listed down below? And how do they differ, meaning how do they operate? At first, the low-pass filter allows low frequencies to pass. Usually the application is for voice signals, okay? While blocking away or filtering out noise signals. High-pass filters is the exact opposite, which means that it allows only high frequency, for example, for a modulated signal, it allows only high frequencies to pass through while blocking lower frequencies. Band-pass filters allow only frequencies within a range, bandwidth, to pass while blocking from above and from below different frequencies that would occur outside of this window, and notch filters. Low-pass filter. So low-pass filters allow low-frequency signals to pass while attenuating high-frequency noise. A simple RC low-pass filter has the transfer function given by H omega is equal to 1 divided by 1 plus J omega RC. The cutoff frequency is FC is equal to 1 divided by 2 pi RC. R is the resistance, C is the capacitance, and Fc would be the cutoff frequency. Now, what does this mean? Cutoff frequency, which is given by Fc is equal to 1 divided by 2 pi Rc, is the frequency at which or below which any frequency would be accepted. Otherwise, So for the values that are above that, since we are talking about a low-pass filter, any frequency above FC would be cut off, would be clipped and removed by the filter, so it would not show up or show out within the output of the filter. Now, if we diagnose this transfer function, so we need to measure or assess what frequencies would pass through based on the limit calculus, okay? So if we evaluate the limit of h omega, which is the transfer function, when the frequency increases, if you notice the frequency is within the denominator here, so it's part, by the way, of omega, which is omega is the pulsation, omega is equal to 2 pi f. So as the frequency increases, this function decreases, okay? It tends to 0, okay, as the frequency grows to infinity. So, in other words, only for lower values of frequencies, this function would be relevant because it would produce an amplitude of a signal that is not 0, that is acceptable. Meanwhile, for higher frequencies, it becomes 0. So only lower frequencies would appear at the output having relevant amplitude values. High-pass filter. High-pass filters allow high-frequency signals to pass while blocking low-frequency components. So you would have a higher number at the numerator, unlike the low-pass filters. The transfer function is given by h omega is equal to j omega rc divided by 1 plus j omega rc, where the cutoff frequency is also given by fc is equal to 1 divided by 2 pi rc. The difference here is any frequency below this one would be clipped, would be cut off, okay? Only higher frequencies would be accepted. Going back to the same concept of analyzing the transfer function based on this equation, okay? To assess what frequencies would be kept or what frequencies would be removed based on this equation. So we estimate that or we assess that based on limit calculations. So if we notice here within this function, within this equation, you have omega in such case both in the numerator and the denominator. So when you have high frequencies and both in the numerator and the denominator, the h omega would tend to 1, okay? So for high frequencies, you would get 1. So a perfect transfer function for the amplitude, okay? But for lower frequencies, so you would get 0 in the numerator, 0 in the denominator. Of course, the extreme case would be a 0 frequency. But the point is, for very low frequencies, you would get something close to 0, both in the numerator and the denominator. What remains is 1 here. So HW would give you 0. So the amplitude, in other words, for lower frequencies would be very close to 0. It would be negligible. This would allow this filter to dim down and choke lower frequencies. Meanwhile, higher frequencies would survive. Why? Because they would satisfy one, let's say here you have j omega rc divided by j omega rc for high values, okay? Both of them would remain and you would get something like 1 divided by 1 plus 1, okay? Because j omega rc divided by j omega rc, this becomes, by the way, for higher frequencies, this becomes negligible and the limit becomes 1, okay? So h omega would be equal to 1, which means that such high frequencies would survive the filter and remain after filtering. Analog to digital conversion. Need for analog to digital conversion or ADC. Most sensors generate analog signals that cannot be codified, while modern data acquisition and control systems, SCADA, by the way, another word for it, operate digitally. So analog to digital converters, ADCs, convert continuous analog signals into digital values that can be numerized and coded and sent as a binary sequence. They can be recorded, they can be compressed, etc. Quantization. The analog signal is represented by discrete digital levels. The number of these levels would be the maximum number of values that can be codified within the system, and these would determine the resolution of the system, okay? How much accurate? So with a larger number of levels accepted, okay, there would be a higher resolution and vice versa. The resolution of an ADC or analog to digital converter is determined by the number of bits n, with capital N is equal to 2 power n, with n is the number of bits and capital N is the number of quantization levels. As an example for that, let's say you have 1, 2, 3, 4, 5, 6, 7, 8, let's say, okay? We have 8 quantization levels. How many bits do we need in order to code these 8 levels? That would be 2 to the power of n is equal to 8. Now, of course, nothing to the power of n might be equal to 10, okay? At times you have a specific number of or quantization levels that would not be exactly equal to all the values that can be coded by 3 bits or 4 bits or 5 bits, etc. Okay, but in such case you would choose the highest number of bits that would at least like code this number of values or above. Okay, so let me digress a little bit. For 8 values, how many bits do we need to code 8 values? 2 to the power of n is equal to 8, so n would be 3. Okay, 3 bits. And we got that through guessing. But there's a way to solve this problem mathematically. We're gonna get to that in a moment. So let's check if 3 bits would be sufficient in order to code 8 values. So you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. These should be 8 values. These are 4, and these are 4. So 8 values can be coded, and these are all the possible combinations that you can get with 3 bits. Now, how can we solve it mathematically? Okay, so you need to place a Neperian log behind each of the values, to the left and to the right, within this equation. So ln 2 to the power of n is equal to ln 8. Now we know that 8 can be written as 2 to the power of 3, right? So ln 2 to the power of n is equal to ln 2 to the power of 3. 3 can be placed behind the log here, and n also can be placed behind the log. So n ln2 is equal to 3 ln2. Log 2 can be factored out, and hence n is equal to 3 bits would be the final answer. Now, let's say we have 10 values that we need to code, okay? So 2 to the power of n is equal to 10 values. There is no n value that would give you exactly 10, okay? But we need a minimum of 10. So 3 won't work because it codes 8 values. 4 would give us 16 values. That would be enough. So you can code 10 values with an extra 6 that would be like reserved, okay? So again, for n is equal to 4, you would get 16 values. So 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. Yeah. 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Then 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. These are 16 values. By the way, in case you are wondering how am I running all of these combinations. This is how. We need to add 1 with XOR addition. What is XOR addition? XOR addition is when you add 1 to 1, it gives you 0 with a return. Okay? So anything added would give you 1. Okay, I'm sorry. You have 1 plus 0 and 0 plus 1. So only when the bits are different, you get a 1. So 1 XOR 0 or 0 XOR 1 gives you 1. But 0 XOR 0 gives you 0. And 1 XOR 1 gives you 0 with a returned 1. So here, when you have 1 plus 1, okay, you have 0 and a return of 1, which is placed on the second level to the left, okay? Because the low weight is to the right and the high weight is to the left. Speaking of resolution, the voltage resolution is given by delta V is equal to Vref or V reference divided by 2 to the power of n, where Vref is the reference voltage and 2 to the power of n is all the possible values that we can get based on the number n of bits available. Sampling, according to the Nyquist sampling theorem, the sampling frequency must be at least twice the maximum frequency present in the signal. So Fs should be at least greater than or equal to 2 times F max, where Fs is the sampling frequency and F max is the highest signal frequency. To give you a picture concerning Nyquist, so let's say the signal is this. The frequency of the sampler should be at least 2 pulses, okay, which means like that, okay, in order to be effective. Of course, usually for a much better resolution, it would be much higher than that, okay, but the Nyquist criteria means that at least the very least minimum is that the sampling frequency should be at least, at the very least, twice the frequency of the message that is to be sampled. Noise reduction. Sources of noise. Sensor signals can be affected by several types of noise, including thermal noise due to high temperature surrounding the sensor, shot noise, electromagnetic interference due to existing environmental magnetic fields, and quantization noise, which means that when you have a quantizer, let's say for example, these are the different levels of quantizations, correct? But when the value falls in the middle between 2 quantization values, okay, there would be an error, which is, by the way, the maximum error here is equal to the distance of quantization separating 2 consecutive levels where this sample is falling, divided by 2. That would be the maximum quantization error. All right? So we need to increase the resolution, but as much as you increase the resolution, still you can get errors. Why? Because there would still be a distance between different quantization levels. That's why for higher resolutions, you would have a much larger number of quantization levels to produce a more accurate reproduction of the original signal. A side note concerning shot noise. Shot noise has to do with the nature of the electron, which means that when you have a flow of electrons, for example, being received by a sensor, that flow would not be consistent from the first reception moment, okay? It would gradually increase until a specific saturation of the head, and this is when truly the signal is triggered at the output, if we're talking about this type of reception. Or also the photon, when you have a photonic reception that is triggering the release of electrons in a current flow that would be detected and understood as the flow or the flux of light being received, okay? The reception of these photons and also the release of the electrons would not be as uniform as you would expect Why? Because you would have at the first contact a small excitation, a small release of electrons, but then afterwards the release would become more effective and more analogous and like accurate, reflecting the trigger, the input, accurately at the output level. So that would be the problem, the inconsistency, so to speak, between the input and the output. Thermal noise. The thermal noise is generated by the random motion of electrons in resistive components. Actually, the thermal noise is a phenomena that often occurs within receiving devices such as receiving antennas and different electronic components that have to do with transmission, with coding, etc. The root mean square RMS voltage of thermal noise is given by Vn is equal to square root 4k TRB, where k is a Boltzmann constant given by 1.38 times 10 to the power minus 23 joule per Kelvin. T is the temperature, which is the absolute temperature, also in Kelvin. R is the resistance of the device, and B is the bandwidth. To make it a little bit more simpler, or to elaborate on this kind of phenomena, at first, B is the bandwidth of the signal, frequency bandwidth of the signal being processed by the device. If we're talking, for example, about a transmission or receiving device, the signal that's being received is operating within a bandwidth range, correct? Between two frequencies. This is the bandwidth that we are talking about. That's first. Second, now why would a noise signal be created within such a device? What is the origin for that? You see, the resistive characteristics for different electronic components, such as the capacitance, the coil, the resistance, would change due to increase or decrease of temperature. Usually, we're talking here about the increase of heat and temperature. Why? Because due to the dilation of the different components, which is caused by heating, the characteristics such as resistivity of different electronics would change, and this would introduce a current, okay, which is a parasitical current, which would be a noise current, noise signal. This is called noise power within the electronic device, and it is measured by this kind of equation. So it's dependent of the temperature involved, the resistance of the component, and the bandwidth at operation. SNR, or signal to noise ratio. The quality of a sensor signal is often evaluated by the SNR factor, okay, or SNR parameter. SNR stands for signal to noise ratio. It's given by P signal, the power of the signal, divided by the power of noise. So it is the ratio between the signal power and the noise power. Usually, due to the fact that you would have different very high or very low ranges, we need to measure it, or it's preferable to measure it in terms of decibels. And the formula would be SNR in dB is equal to 10 log base 10, because log base 10 has a very high range, so it changes very slowly for high rates of change, for high gaps between P signal and P noise. So it is 10 log base 10 power of signal divided by the power of noise. Higher SNR values correspond to much higher quality or much better signal quality. To give you an example on why it is necessary to use the logarithmic scale, let's say you have a transponder within a satellite located at 35,000 kilometers above ground level, okay, above the Earth. The signal, if it's being emitted at 2 watts power, it will arrive due to attenuation and very long distances traveled. It would arrive at an Earth station with a power of 10 to the power of minus 13 watts. So it would attenuate so enormously, okay, that if we want to evaluate it in terms of watt, okay, it would be irrelevant, because the gaps of the different values would be so wide, okay? And for these very large or very small values, the calculation, if it's done in a classical way, it's not humanly processable, okay? So we need a more practical value. So instead of evaluating the value as a million or thousand or like that, we evaluated by using the log base 10, which actually would replace the signal drop by the power for that drop. Let me explain it a little bit further. So let's say you have 10 to the power of 6. Instead of placing 10 million as a value, we place 6 as a value. And we're going to see it in how the log base 10 would evaluate 100, 200, what we would get from that, etc. So let's say that the power of the signal is 10,000. Power of the noise is 10. Okay? So SNR, this of course is a benign example. SNR is equal to 10 log base 10 of 10,000 divided by 10, which would become 1,000. Now, 1,000 can be written as, so 10 log 10, 1,000 can be written as 10 to the power of 3. Now, log 10 is equal to 1, but 3 can be removed and placed behind the log, so you would get 10 times 3, 30, log base 10 of 10. Log 10 is equal to 1. So this would be completely removed, and the final answer is 30. This is the final answer. Noise reduction techniques. Common noise reduction techniques include shielded cables to protect the wiring from electromagnetic interference and induction of currents due to external magnetic sources or shifting magnetic fields that are external, differential measurement, filtering, signal averaging also through approximation, and proper grounding, which is very important as well, in order to remove any electrical surge within the electronic component. Wheatstone bridge circuits. Bridge circuit principle. The Wheatstone bridge is a widely used circuit for measuring small resistance changes in sensors such as the strain gauges, pressure sensors, and temperature sensors, RTDs. The bridge consists of 4 resistors arranged in a diamond configuration like that, okay? 2 opposite nodes are connected to a voltage source Vs, and the output voltage is measured across the other 2 nodes. The output voltage of the bridge is given by VO, which is V out, is equal to Vs multiplied by R3 divided by R3 plus R4 minus R2 divided by R1 plus R2. Vs is the supply voltage, R1, 2, 3, 4 are the bridge resistances, and VO is the bridge output voltage. Balance the bridge. The bridge is balanced when R1 divided by R2 is equal to R3 divided by R4. Under this condition, VO is equal to 0. When one of the resistors changes due to a physical stimulus, such as a strain or temperature, the bridge becomes unbalanced, producing a measurable output value, output voltage. This output would be measured to reflected as a change of pressure or whatever physical parameter that we are measuring. Small signal approximation. If one resistor varies by a small amount, delta R, the bridge output becomes approximately proportional to the resistance change. VO is approximately equal to Vs divided by 4 times delta R divided by R. This linear relationship makes the Wheatstone bridge very useful for precision sensor measurements. Final summary: signal conditioning is an essential step in sensor systems. Raw signals from sensors often require amplification, filtering, and noise reduction before being converted into the digital form. Amplifiers increase signal strength, filters, remove unwanted frequencies, and ADCs or analog to digital converters enable digital processing. Wheatstone bridge circuits are particularly important for sensors that detect small resistance variations, such as strain gauges and pressure sensors. Chapter 11 or Module 11, Smart Sensors and Sensor Networks. Traditional sensors typically generate raw analog signals that require external signal conditioning or adaptation and processing. In contrast, modern sensing systems increasingly rely on smart sensors, which integrate sensing elements such as the captors with signal conditioning or adaptation, processing, and digitization. Okay, meaning conversion from analog to numerical to binary, plus communication capabilities to transfer the system or the signal value being measured. So, smart sensors are capable of performing functions such as self-calibration or adaptation, self-diagnosis, so they can test if they are working or not, digital communication with a base, and local data processing. When multiple sensors are interconnected and exchange data through communication networks, they form sensor networks. These networks enable distributed sensing and are widely used in applications such as environmental monitoring, industrial automation, and smart infrastructure. So they act just like different computers connected under the same network or different mobile phones under the same coverage that can actually communicate among each other and with the base or with the core network. Integrated sensors. Definition: integrated sensors combine sensing elements, signal conditioning circuits, and sometimes digital processing units within a single semiconductor chip. Advances in microelectronics and microelectromechanical systems, which are the MEMS technology, have enabled a miniaturization and integration of sensors, such as the sensors that you have on your own smartphone. A typical integrated sensor includes sensing element, which is the captor, analog signal conditioning circuits that condition or adapt the signal by amplification, filtering, etc. ADC or analog to digital converter, which converts the analog signal into a digital binary signal, and digital interface, which relays the information being measured to a base or to a remote electronic board through a communication device. MEMS-based sensors. Many integrated sensors are based on MEMS technology, which allow mechanical structures to be fabricated on silicon substrates. Examples include accelerometers within your smartphone, gyroscopes also, and pressure sensors. For example, the capacitance of a MEMS capacitive sensor is given by C is equal to epsilon A divided by D, where C is equal to capacitance, epsilon is equal to permittivity of the medium, A is the electrode area, which is the area of one of the plates, positively or negatively charged plates, and D is the separation distance. As the pressure increases, for example, the compression would cause a drop in the distance or a decrease or narrowing down in the distance between the plates, which would increase the capacitance because they are inversely proportional, increasing the current also that's being generated, and vice versa. So for lower pressure, you would have a dilation, okay? So the place would become more relaxed, the distance would increase, and this would decrease the capacitance, leading to a lower current. If displacement x changes the gap d, the capacitance becomes Cx is equal to epsilon A divided by d minus x. This change in capacitance can be converted into an electrical signal representing physical displacement. In the pressure sensing application, this would be caused by an increase of pressure, which would contract the distance between both of the electrodes or the plates, and this would reflect in a change of an electrical signal. Okay, and vice versa for lower pressure, this distance would increase, so it would be d plus x, so that would decrease the capacitance, leading to a lower current. Advantages of integrated sensors: compact size, lower power consumption, so they don't have a high power requirement, they don't consume a lot of energy, high reliability, meaning that their values are trustworthy, and reduced noise due to short interconnections. Microcontroller-based sensors concept. Microcontroller-based sensors integrate a sensing element with an MCU or microcontroller unit that performs data processing and control tasks. The microcontroller may perform the following: signal processing, analog to digital conversion, for example, data filtering to remove any noise, calibration, adjustment, and communication, which is transferring the data to another platform, another circuit, or to an antenna. The last part, by the way, would include modulation, especially when we're talking about long distances, which means that the data should be transferred on a high frequency carrier. Okay, in other words, let's say the data is like this. Okay, so 101, something like that. Let's say that the coding is NRZ. So these ones and zeros would be multiplied by a high frequency carrier, which would shift in phase or amplitude, okay, before being transmitted. So let's say, for example, this wave would become something like this, where high frequency sections would be considered as 1 and low frequency sections would be considered as 0, okay? Or based on the phase change, such as in PSK or phase shift keying modulation. In such case, you would be changing the phase in order to infer the change or like the modulation of data, okay? In order to carry or hide sequences of ones and zero within the high frequency carrier. This is why we call it carrier, because it is not the high frequency itself that's the information. It is carrying the information, the data of or sequences of zeros and one on the inside of it, okay, being hidden in one of the parameters such as frequency, phase, or amplitude. The sensor output is often digitized using an internal ADC or analog to digital converter. D is equal to Vn divided by Vref multiplied by 2 to the power of n minus 1. Vn is the measured voltage. Vref is the reference voltage. Okay, multiplied by 2 to the power of n minus 1, with n being what? The number of bits required to code all the values that this sensor can measure. Okay, now why 2 to the power of n minus 1? Because you need to remove, so 2 to the power of n would be all the values possible, minus 1 because any value that is a sequence of zeros should not be considered. Why? Because what if there was a power cut? Okay, a sequence of zeros should not be considered as a value, okay, because it would be, in one of the cases, implying that you had a power cut or a disconnection of the sensor. Okay, it should not be read as a valid possible value. Embedded processing. Microcontrollers can implement algorithms for signal analysis. For example, averaging can reduce measurement noise. X bar is equal to 1 divided by n, that's the average. Sigma I is equal to 1 to n xi, meaning that the average of different values that are being collected is equal to the sum of these values divided by their number, where xi is equal to individual measurement samples, n is the number of samples, total number. Digital filtering algorithms may also be implemented directly within the microcontroller. Communication interfaces. Microcontroller-based sensors typically provide digital communication interfaces such as I2C, SPI, UART, and CAN bus. Okay, these interfaces allow sensors to communicate with another device. Okay, that would be the medium or like the plug through which it would be able to communicate. So this can be another device or control system. IoT sensors, Internet of Things or IoT, these refer to network of interconnected devices capable of collecting data and exchanging among each other and with a network also, okay, with the internet. IoT sensors combine sensing capabilities with communication modules that transmit data online, okay, to remote servers or cloud platforms. IoT architecture, a typical IoT sensing system includes the following layers: sensing layer, communication layer, data processing layer, and application layer. So they can have an application also, okay, a software. Energy consumption. Energy efficiency is an important factor for IoT sensors for durability, especially for battery-powered devices, okay, that are wireless. The energy consumption of a sensor node can be expressed as E is equal to P multiplied by T, where energy consumption is equal to power consumption multiplied by the operation time. So that would give us how long it can operate before the requirement to change the battery. For wireless communication, the energy required to transmit data is often modeled as EKT. So energy of transmission Tx is a subject of two parameters, K, which is the number of bits to be transmitted, and D, or the distance of transmission. This energy is equal to E-elec, or the energy consumed by electronic circuitry, multiplied by the number of bits to be transmitted, plus the amplifier energy constant E-amp, or epsilon amp, times K, again, the number of bits, times the distance to the power of n, where n is the path loss exponent. Common IoT communication technologies. IoT sensors may use several wireless communication technologies, such as Wi-Fi, Bluetooth Low Energy or BLE, Zigbee Low WAN or a WAN, Wide Area Network, and IoT. Okay, each technology provides different trade-offs in terms of range, power consumption, and data rate. So, for instance, for the Bluetooth, it has a very low range of around 10 meters. Okay, it requires some degree of visibility, but it's kind of robust, but it doesn't have a longer range compared to Wi-Fi. Wi-Fi can be like detecting the sensor for a much longer distance. You have Zigbee, you have NB-IoT. Now, one of these is ad hoc based. Ad hoc meaning that the sensors can communicate directly with each other, okay, from one to another in sequence. So they form a network of their own. Low-ray WAN, WAN meaning wide area network, that would be also a unique different architecture, and NB-IoT. Concerning NB-IoT, which stands for Narrowband IoT or Internet of Things, this is a cellular technology that uses the concept of LPWA or low power over a wide area transmission. So it can transmit data given that they are like smaller data blocks for sensing measurements for longer distances, okay, over a low power consumption. Okay, and usually the application would be for infrequent data measurements, so infrequent communications and sensing. It should not be very consistent, otherwise it wouldn't be efficient. So it is for a cyclical transmission of data that is infrequent at a low power for longer distances. Concerning Zigbee, that would be a low power, low data rate mesh networking technology where sensors communicate among themselves and they form a mesh network where they communicate among each other. Okay, so they have their private network, so to speak. So similar to the ad hoc technology where one sensor would send the data to another one to another one. This is how they form their own network. And like each IoT component would be a part of the communication path. Wireless sensor networks. A wireless sensor network, WSN, consists of a large number of distributed sensor nodes that communicate wirelessly to monitor environmental or physical conditions, such as temperature sensors scattered around a large area. Each sensor node typically includes sensor unit, processing unit, communication module, and power supply. Of course, if there's no possibility to get power, they would be replacing the power supply with the battery, or actually the battery is always there, but there would not be a power supply available for such application. An alternative for an external power supply in case a power grid is not available in the area is to use a miniaturized solar panel so as to feed the sensor with solar energy. Okay, this way you can guarantee that the sensor would keep going and operating even in the cases of unavailability of external power source. Network topologies. We have three types of topologies. The star topology, where you have a central hub and all of the surrounding sensors would report to the center. Mesh topology, where different sensors would communicate among each other. Each one can communicate the other ones. That would be a stronger architecture. And tree topology, where you have the head and the head would distribute to others. So there would be a hierarchy. In mesh networks, nodes relay data through intermediate nodes to reach a central base station. So as a representation for that, in a star topology, you have the base station in the middle, and all the different sensors are connected to the base station. Now, in case it goes down, all the sensors would be disconnected, correct? In case the center go down. Now, for mesh topology, in mesh topology, different sensors communicate among each other. So there would be like a large number of routes through which the data can be transmitted among these different sensors. That would be of a very high effectivity, okay, and very reliable. Now, for the tree technology or tree topology, you would have something like this. So, something like a hierarchy. Now, the problem with the tree topology is that in case one of the nodes at the branches goes down, the entire branch would be cut off from the center, from the hub. Let's say this is the main central hub. Data aggregation. Sensor networks often perform data aggregation to reduce communication overhead, meaning that multiple data info would be aggregated together and sent in one block. This means that both the temperature and the humidity plus other sensor values, let's say pressure, all of that would be aggregated in one information block and sent all together in one transmission. The aggregated data may be computed as DAG is equal to F, which is the function of D1, D2, all the way to the N, where the I represents measurement or measurements from individual nodes. A simple aggregation example is averaging. D average is equal to 1 divided by N, sigma I equal 1 to N, Di. Coverage and connectivity. The coverage area of a sensor node can be approximated as A is equal to pi r square, where r is the range or the distance at which this device can sense, okay? Or sensing radius. How much distance it can cover, and of course, it would be covering in a circle, okay? In a topological circle. Ensuring adequate coverage and network connectivity is essential for reliable operation and communication. Applications of smart sensors and sensor networks. Smart sensors and sensor networks enable advanced monitoring and automation capabilities across many sectors. You have smartphones or smart homes rather that use interconnected sensors to automate household functions and improve energy efficiency. For example, temperature sensors, motion detectors, light sensors, and smoke detectors. Energy management systems often calculate energy consumption as E is equal to sigma I equal 1 to N PITI, which is the power consumption of a device multiplied by the operation time for all the devices. So the sum of the energies of all devices would give us the total energy consumption required. Industrial automation. In industrial environments, sensor networks enable real-time monitoring and predictive maintenance. Applications include machine condition monitoring, process control, fault detection, and asset tracking. Predictive maintenance may rely on vibration monitoring using statistical analysis of sensor signals. Smart cities. Smart cities deploy large-scale sensor networks to improve urban infrastructural services and infrastructure. Examples include traffic monitoring systems, air quality monitoring, smart street lighting, and waste management systems. Urban sensor networks collect large volumes of data that can be analyzed and processed in order to optimize resource usage and improve quality of life. Let's talk a little bit about the pass loss right now. Okay, let's say you have a Wi-Fi access point. How do we measure the pass loss for the signal from the transmitter all the way to the receiver? That would be your mobile phone or your sensor in such case. The antenna gain, by the way, which increases by 2% with dual antenna Wi-Fi modems. You have the pass loss is equal to TX power, transmit power, minus cable loss, which is the loss within the cabling, if you have a cabling system, plus antenna gain, which is what we referred to moments ago, minus the RX sensitivity, the sensitivity for the receiving device, minus the fade margin. Now, the fading margin has to do with the type of barrier that is in place, such as air, wooden doors, glass, etc., which increase the signal attenuation and need to be factored in within the pass loss equation. So, the pass loss should not go above a specific threshold for the signal to be received or for the receiver, the sensor, to be sensitive for the signal that is being transmitted by the antenna. Finally, smart sensors integrate sensing, signal processing, and communication capabilities within compact devices. When connected through communication networks, these sensors form distributed systems known as wireless sensor networks. Such technologies enable advanced monitoring and automation across various domains, including smart homes, industrial automation, and smart cities. Advances in microelectronics, embedded systems, and wireless communication continue to expand the capabilities and applications of smart sensing technologies. Chapter or Module 12, Sensor Calibration and Error Analysis. Accurate measurement is fundamental in sensor-based systems. However, real sensors are never perfectly accurate due to imperfections in fabrication or manufacturing in sensing elements. Also, you have environmental influences, interference, electronic circuitry, and measurement methods. Sensor calibration and error analysis are therefore essential processes used to quantify, correct or rectify, and minimize measurement errors or deviations. Calibration ensures that the sensor output corresponds accurately to the physical quantity being measured, while error analysis evaluates the uncertainty and reliability of the measurement device. Measurement error. The error in a measurement is defined as the difference between the accurate real value and the measured value. So error is equal to measured value minus true value. If the measured value is denoted by xm and the true one is denoted by xt, the error becomes xm minus xt. Errors can be positive or negative depending on whether the measured value is larger or smaller than the true value. Relative error. Relative error expresses the magnitude of the error relative to the true value. Epsilon r is equal to error divided by true value, with error being xm minus xt, which is the difference between the measurement and the true, or the measured value and the true value. Divided by xt, which is the true value, give us the error rate, which is epsilon r. Relative error is often expressed as a percentage, so you simply multiply this quotient by 100. So ER in percent is equal to xm minus xt divided by xt times 100. Relative error is useful when comparing measurement accuracy across different scales. Let's give a small example or application for that. So given a measurement device for temperature, it measured the temperature value for an environment and it gotten 15 degrees, let's say, okay? Meanwhile, the true value happens to be 10. Okay, so epsilon r is equal to 15, which is the measured value, minus 10, divided by the true value, which is 10. So this is equal to 15 minus 10, which is 5 divided by 10, or 1 divided by 2. Okay, equal to 0.5. As a percentage, you simply multiply that by 100. So ER in percent is ER times 100 equal to 50%. So you have a 50% error. That would be, of course, a very extreme case. Calibration techniques. Purpose of calibration. Calibration is the process of comparing the output of a sensor with a known reference standard to determine its accuracy and correct any deviations. The calibration process establishes a relationship between the sensor output signal, which is Y, and the actual physical quantity X. So it is given by Y is equal to f of X. In many sensors, the relationship can be approximated as linear. Y is equal to AX plus B, where A is the sensor sensitivity and B is the offset or bias. Calibration determines these parameters so that the sensor output can be adjusted and corrected. Calibration methods. Several calibration methods are commonly used in sensor systems. Single point calibration. A known reference value is applied to the sensor and the output is adjusted accordingly so as to remove the deviance between the true value and the measured value. If the expected output is YT and the measured output is YM, the offset is equal to YM minus YT. That offset should be adjusted in order to remove this deflection from the true value. That would be the B parameter within Y is equal to AX plus B equation, which is, by the way, mathematically is called the Y-intercept. The sensor reading can then be corrected by subtracting this offset. Two-point calibration. Two known reference values are used to determine both offset and sensitivity. Let the calibration points be x1, y1 and x2, y2. The slope sensitivity, which is, by the way, A within Y is equal to AX plus B equation. A is equal to rise over run. Okay? How much the function or the line equation is rising in respect of the x distance being traveled. So A is equal to y2 minus y1 divided by x2 minus x1. The offset B is equal to y1 minus ax1. Thus, the calibrated sensor model becomes Y is equal to AX plus B. Now, let's say you have 2 points. This is a representation of A. So, point 1 is, for example, M, point M, having coordinates x1, y1. x1 is here. y1 is the elevation. Another point, N, having coordinates x2, y2. This is x2, and this is y2. The slope is simply tan x or tan theta, the tangent, which is the opposite segment within this triangle, rectangle triangle, divided by the adjacent segment, okay, or rise over run. Okay, the opposite would be y2 minus y1. This is the distance, the opposite distance, okay, and the traveled, this is the elevation rather, and the traveled distance for this segment, the length of this segment, is x2 minus x1. So tan theta, the tangent of theta, is equal to rise over run, which is this segment length divided by this segment length, equal to y2 minus y1 divided by x2 minus x1. And this can also be written as A. Multi-point calibration. For nonlinear sensors, several calibration points are used to construct a calibration curve. Polynomial fitting or interpolation methods may be used, so y is equal to a0 plus a1x plus a2x squared, etc. This method improves measurement accuracy over a wider range. One of the ways to do calibration in such case would be interpolation, and that would be the method. So y is equal between 2 points, the approximated y1 plus x minus x1 multiplied by y2 minus y1 divided by x2 minus x1, which would be the rise over run. Systematic and random errors. Measurement errors can generally be classified into two main categories: systematic errors and random errors. Systematic errors, these are consistent and repeatable deviations caused by known or unknown factors. Common sources include sensor miscalibration, environmental influences, instrument bias, and mechanical misalignment for motion sensors or displacement sensors. If a systematic error B is present, the measured value becomes xm is equal to xt plus b, which is the bias. Because systematic errors are predictable, they can be rectified easily. So they can be often corrected through calibration. Random errors. Due to their random nature, they are harder to cope with and to rectify because they are unpredictable. Random errors arise from unpredictable variations in the measurement process. They may result from electronic noise, environmental fluctuations, thermal variations, and mechanical vibrations. Random errors cause measurements to fluctuate around the true value. The statistical properties of random errors are often described using the mean and standard deviation. The mean of n measurements is x bar is equal to 1 divided by n, sigma I equal 1 to n xi, and the standard deviation, how much they are deviating from the mean value, is given by sigma square root of 1 divided by n minus 1, sigma I equal 1 to n, xi minus x bar square. X bar, of course, is the mean value. The standard deviation indicates the spread of the measurements around the mid-average value. Drift. This parameter here refers to a slow change in sensor output over time due to decay or depletion or aging, even when the measured quantity remains the same, remains constant. Drift may be caused by aging of components, temperature fluctuations or variations, mechanical stress, and chemical degradation of the material itself. The drift rate can be expressed as d is equal to delta y divided by delta t. Delta y is the change in sensor output and delta t is the time interval. Types of drift include zero drift, offset drift, and sensitivity drift, which is a gain-related type of drift. Periodic recalibration is often necessary in order to compensate for that drift. Noise factor. Noise refers to unwanted disturbances that affect sensor signals and reduce measurement accuracy. Common sources of noise include thermal noise, electromagnetic interference, shot noise, and quantization noise. So for thermal noise, they have to do with the change in temperature that can affect the components or the substance, like the metal oxide within a sensing device. The electromagnetic interference due to a proximity to a magnetic field or power wires, for example, or high electrical power being transmitted around the sensing device. Shot noise also has to do with the transfer of electrons, something like that. And quantization noise, which has to do with the resolution of the sensor, meaning that when you have lower levels of lower quantization levels, there would be a maximum error which is equal to the distance between two consecutive quantization levels divided by 2. So if a value sits in the middle, it can be either of the two, okay? But that would give us a value among these two surrounding values, which is not the accurate value where it was originally detected. It would be snapped to one of the levels in the quantizer. Thermal noise, it is also called Johnson-Nyquist noise, results from the random motion of charge carriers in resistive components. The RMS noise voltage is given by Vn equal the square root of 4k TRB, where k is Boltzmann constant, which is 1.38 times 10 to the power of minus 23 joules per Kelvin. T is the absolute temperature in Kelvin, R is the resistance, and B is the frequency bandwidth. Now, this phenomena is due to the fact that when you have a heating within a receiving device or an electronic component, let's say, or let's consider a reception device, a data reception or an antenna receiving device. The heat or the increase in temperature would change the characteristics of the electronic components. So the resistivity would change within like resistance, within capacitor, within other components, which by the way also have a reactive component to them, which is like dependent on the frequency. So let's say you have a capacitor. The capacitor impedance ZC is equal to R, which is the pure or real part of the resistance, okay? And you have an imaginary part because it is a complex number. That would be the reactance called XC, okay? XC, the reactance, which is the imaginary part of the impedance, is equal to 1 over 2 pi square root of RC, I think, okay? Where C is the capacitance. Okay, 1 over 2 pi F square root of RC, something like that. I don't remember exactly, but you see, it is dependent on the frequency. So when the impedance change due to an increase of temperature, the frequency component would change. This would change the entire signal being processed, okay, and introducing a thermal noise. The power of noise is Vn here, okay, within this formula. So you have a parasitical noise being generated due to heated conditions, which is equal to the square root of 4kTRB. As a correction, the reactance of the capacitor is given by Xc is equal to 1 divided by 2 pi Fc. And F is the component, of course, that would change due to the change of the capacitance, which is subject to the temperature fluctuation. So at high temperatures, the impedance of the component would change. This would also reflect in a change of the capacitance and the reactance, basically. That would also affect the frequency of operation, creating a noise signal, a parasitical noise signal that would interfere with the original signal. That would create an error within the receiving or the sensing device. Signal to noise ratio. The signal to noise ratio measures signal quality. SNR is given by power of the signal divided by the power of the noise. So it is a quotient or a ratio. Expressed in decibels, it gives us 10 log base 10 P signal divided by the power of the noise, which is more effective and more practical when dealing with infinitesimally small signal to noise ratio. The signal to noise ratio or SNR measures signal quality, which is the quotient or the ratio between the signal of the message divided by the power of noise, okay? Power of the signal divided by the power of noise. Usually, it is more effective to measure it in decibels, which means when we use the logarithmic scale, we can get a more moderate value when you have a large gap between like outputs, okay? A large gap of values being measured. For example, let's say you have values of 10 to the power of minus 13 or 165 millions, okay? So it would be better to measure the value in logarithmic scale or in decibel. This would be given by SNR in dB is equal to 10 log base 10, power of the signal divided by the power of noise. Higher SNR values indicate better measurement qualities, of course. As an example, let's say that the power of the signal is equal to 100 millions, 106 zeros after it. The power of noise equal to 100. So SNR becomes 100 million, so 100 times 10 to the power 6 divided by 100. So the answer would be 1 million or 10 to the power of 6. You see, this value is not nominal, it is very large and unpractical. So in order to make it more practical, we use the logarithmic scale. So what does it become in logarithmic value, okay, in decibels? SNR in decibels is equal to 10 log base 10 of power of signal divided by power of noise, which is 10 to the power of 6. Now 6 here can be multiplied behind the log. This is how we can remove it. So we get 10 times 6 times log base 10 of 10. This quantity here is equal to 1. So we are left with 10 multiplied by 6, or 60 decibels. So instead of representing the value, we are actually representing the exponent of the value. This is how much reduced the logarithmic value is in respect of the original value, which makes it more nominal and more practical to work with. Error propagation: when a measured quantity depends on multiple variables, each with its own uncertainty, the resulting uncertainty must be determined using error propagation. Suppose a quantity y depends on several measured variables, so y becomes a function of different uncertainties fx1, x2, xn, or different values that can have uncertainties altering the accuracy or affecting the accuracy of the output value. The combined uncertainty in y is approximated by sigma y is equal to the square root of the partial derivative of y in respect of x1, x2, xn times sigma x1, which is the uncertainty for each xy, okay? So sigma x1 is for variable x1, x2 for x2, etc. square. So as we have more dependencies on more variables, this would increase the error amount for the output. Example, product of variables. If y is equal to x1 times x2, the relative uncertainty becomes sigma y divided by y is equal to the square root of sigma x1 over x1 squared plus sigma x2 over x2 squared. Error propagation is essential when multiple sensor measurements are combined together to produce one output or one result in calculations. Summary: sensor calibration and error analysis are essential for ensuring accurate and reliable measurements. Calibration establishes the relationship between sensor output and the true physical quantity being measured, while error analysis quantifies uncertainties arising from systematic errors, random errors, drift, and noise. Understanding these factors allows engineers to design more precise measurement devices or measuring systems and implement appropriate correcting, adjusting techniques, and also compensation techniques. At the end, thank you for watching and see you next time.